Good evening, everyone. As the day fades and the world around you settles into quietness, I invite you to join me on a journey into the deepest mysteries of the cosmos. Tonight, we're venturing into realms where the very fabric of reality bends, breaks, and transforms. We're exploring black holes, those enigmatic cosmic monsters where space and time themselves fall apart. Before we begin this cosmic odyssey, I invite you to like this video and subscribe to give me more motivation to continue bringing you these deep explorations of our magnificent universe. And now, let's drift into the dream of exploring the vast cosmos together with Astromind. Close your eyes if you wish. Relax. Let your mind wander beyond the boundaries of your everyday world, past the familiar stars in our night sky, past the swirling spiral arms of our galaxy, into the places where physics becomes strange and wonderful, where the rules we take for granted simply cease to apply. Chapter 1: The Invisible Monsters. Imagine, if you will, an object so dense, so massive, that not even light can escape its gravitational embrace. A cosmic trap from which nothing returns. Not matter, not energy, not even the fastest thing in the universe. Light itself, traveling at 300,000 kilometers per second, finds itself powerless against this invisible leviathan. These are black holes, and they represent one of the most profound predictions of modern physics. They're places where Einstein's equations take us to the very edge of comprehension, where the smooth geometry of space-time becomes infinitely curved, where past, present, and future blur into something we can barely conceptualize. What makes black holes so extraordinary isn't just their extreme nature, it's that they challenge our most basic assumptions about reality. We're used to a universe where cause precedes effect, where time flows steadily forward, where space provides a stable stage for events to unfold. But near a black hole, these comforting certainties evaporate like morning mist. Time slows down, then stops entirely. Space curves back on itself. The future becomes as inevitable as a direction in space. Yet for all their strangeness, black holes are real. They're not just mathematical curiosities or science fiction fantasies. They exist throughout our universe, from stellar mass black holes weighing a few times more than our Sun, to supermassive behemoths containing billions of solar masses lurking at the centers of galaxies. Our own Milky Way harbors one such giant at its heart, Sagittarius A star, a black hole containing over 4 million times the mass of our Sun, around which hundreds of billions of stars, including our own, perform their slow cosmic dance. The history of black holes is a story of human imagination pushing against the limits of the possible. The idea that gravity might be strong enough to trap light isn't new. Back in 1784, the English natural philosopher John Michell proposed the existence of what he called dark stars, celestial bodies so massive that their escape velocity would exceed the speed of light. He based this on Newton's theory of gravity and the then popular idea that light consisted of particles that could be affected by gravitational force. Michel's dark stars remained a curiosity, a theoretical oddity that seemed to have little connection to the real universe. Over a century passed before the idea resurfaced in a more rigorous mathematical form. The transformation came through the work of a German physicist stationed on the Russian front during World War I, a man named Karl Schwarzschild. In December 1915, just months after Albert Einstein published his general theory of relativity, Schwarzschild did something remarkable. While serving in the German army, while suffering from a painful autoimmune disease that would soon claim his life, he found an exact solution to Einstein's field equations. These equations describe how matter and energy curve the fabric of space-time, but they're notoriously difficult to solve. Einstein himself had only found approximate solutions. Schwarzschild's solution described the space-time geometry around a perfectly spherical, non-rotating mass. What he discovered was both elegant and disturbing. His mathematics predicted that if enough mass were compressed into a small enough volume, it would create a region of space-time so severely warped that nothing could escape from within a certain radius. This boundary, which would later be called the event horizon, would mark a point of no return. Cross that invisible line, and even light moving at its maximum speed would find itself pulled inexorably inward, never to emerge again. Schwarzschild sent his solution to Einstein, who presented it to the Prussian Academy of Sciences in January 1916. Einstein was impressed by the mathematical elegance but skeptical that such extreme objects could exist in nature. Schwarzschild died just a few months later, in May 1916, at the age of 42, never knowing that his solution would become one of the most important discoveries in theoretical physics. For decades, the idea remained controversial. Many physicists, including Einstein, believed that some physical process would prevent matter from collapsing to such extreme densities. The mathematics might permit it, but surely nature would find a way to avoid such exotic outcomes. Stars might collapse, but something would stop them before they formed these pathological regions of infinitely curved space-time. The tide began to turn in the 1930s with work by Subramanian Chandrasekhar. While travelling by ship from India to England as a young student in 1930, Chandrasekhar calculated that white dwarf stars, the dense remnants left behind when stars like our Sun exhaust their nuclear fuel, had a maximum possible mass. Above this limit, now called the Chandrasekhar limit, and sitting at about 1.4 solar masses, no known force could prevent further collapse. This was profound. It suggested that for sufficiently massive stars, collapse to something even denser than a white dwarf was inevitable. But what would that something be? The answer came gradually, through the work of many physicists over several decades. In 1933, Walter Baade and Fritz Zwicky proposed the existence of neutron stars, incredibly dense objects composed primarily of neutrons. When certain massive stars exhausted their nuclear fuel, they suggested the core might collapse to form such an object, with the outer layers blown off in a catastrophic explosion they called a supernova. Neutron stars provided one possible endpoint for stellar evolution. But what about even more massive stars? In 1939, Robert Oppenheimer and his student Hartland Snyder published a paper showing that for sufficiently massive stellar cores, even the extreme pressure of degenerate neutrons couldn't prevent continued collapse. The star would shrink past its Schwarzschild radius and disappear behind an event horizon. It would become what we now call a black hole, though that term wouldn't be coined until decades later. Even with this theoretical work, many physicists remained skeptical. Black holes seemed too strange, too far removed from normal experience. They violated intuition at every turn. How could something have no size yet still have mass? How could time stop at the event horizon? How could the laws of physics break down at the singularity? These questions troubled physicists for years. The turning point came in the 1960s, driven by both theoretical advances and observational discoveries. On the theoretical side, physicists like Roger Penrose and Stephen Hawking proved rigorously that singularities, places where space-time curvature becomes infinite and the laws of physics as we know them break down, were inevitable consequences of general relativity under reasonable physical assumptions. The universe, it seemed, really did permit these exotic objects. On the observational side, astronomers began discovering strange X-ray sources in the sky. These sources, eventually understood to be binary star systems where a compact object was accreting matter from a normal star, provided the first strong evidence for stellar mass black holes. The accretion process would heat the infalling matter to temperatures of millions of degrees, causing it to emit intense X-rays before plunging past the event horizon. One of the most famous of these systems is Cygnus Zona, discovered in 1964. Careful observations revealed that the invisible compact object in this system had a mass of about 15 solar masses, far too heavy to be a neutron star. The only plausible explanation was that it was a black hole. By the 1970s, the existence of black holes was becoming widely accepted in the astronomical community. The term black hole itself was popularized by the physicist John Wheeler in 1967. Before that, these objects had been called various things: frozen stars, collapsed stars, dark stars. Wheeler's term captured the essential feature. These were holes in space-time from which nothing, not even light, could escape. The name stuck, and black holes entered popular consciousness. Today, we know that black holes come in different varieties and sizes. Stellar mass black holes, formed from the collapse of massive stars, typically weigh between 5 and several tens of solar masses. Supermassive black holes, found at the centers of most large galaxies, can contain millions to billions of solar masses. There may also be intermediate mass black holes, weighing hundreds to hundreds of thousands of solar masses, though these are harder to find and study. We've even managed to image black holes directly. In April 2019, the Event Horizon Telescope collaboration unveiled the first image of a black hole's shadow, the supermassive black hole at the center of the galaxy M87. In May 2022, they followed with an image of Sagittarius A star, the black hole at the heart of our own Milky Way. These images show a bright ring of glowing matter surrounding a dark central region, the shadow cast by the event horizon. They provide visual confirmation of what mathematics predicted over a century ago. But to truly understand black holes, we need to go deeper. We need to explore the physics that governs them, the strange effects they produce, and what they reveal about the nature of reality itself. Chapter 2: The Fabric of Space-Time. To understand black holes, we first need to understand Einstein's revolutionary idea about gravity. Before Einstein, gravity was thought of as a force, an invisible pull that massive objects exerted on each other across empty space. Isaac Newton's law of universal gravitation, formulated in the late 1600s, described this force mathematically and did so with remarkable accuracy. It explained planetary orbits, the motion of the moon, the behavior of falling objects on Earth, the tides, and countless other phenomena. But Newton's theory had a philosophical problem. How did gravity actually work? How could the Sun, 93 million miles away, exert a force on Earth instantaneously across the vacuum of space? Newton himself was troubled by this action at a distance, and famously wrote that he would frame no hypotheses about it. The mathematics worked beautifully, but the mechanism remained mysterious. Einstein changed everything with his general theory of relativity. Published in 1915, he proposed a radically different view of gravity. There is no gravitational force, he said. Instead, mass and energy curve the fabric of space-time itself, and objects simply follow the straightest possible paths, called geodesics, through this curved geometry. What we perceive as the force of gravity is actually objects moving along these geodesics through curved space-time. Imagine space-time as a vast, flexible rubber sheet stretched tight. Place a heavy ball on the sheet, and it creates a depression, a curvature in the surface. Now roll a marble across the sheet. As it approaches the depression, its path curves. It might spiral around the heavy ball, or if it's moving slowly enough, it might fall into the depression entirely. The marble isn't being pulled by some mysterious force. It's simply following the straightest available path through the curved geometry of the sheet. This is a simplified, two-dimensional analogy for what happens in our four-dimensional space-time. The Sun doesn't pull on Earth with a force. Rather, the Sun's mass curves space-time in its vicinity, and Earth simply follows a geodesic through this curved space-time, tracing out what we observe as an elliptical orbit. But space-time is more than just space. It's a unified, four-dimensional structure where space and time are intimately connected. The same mass that curves space also affects time. Clocks run more slowly in stronger gravitational fields. This is gravitational time dilation, one of the most counterintuitive predictions of general relativity, yet it's been confirmed by countless experiments. For weak gravitational fields like those we experience on Earth or even near the Sun, Einstein's theory makes predictions that are nearly identical to Newton's. The orbits of planets calculated using general relativity are almost the same as those calculated using Newtonian gravity. But there are tiny differences, and these differences provided some of the first tests of Einstein's theory. One famous test involved the planet Mercury. Astronomers had long known that Mercury's orbit didn't quite match Newton's predictions. The point of closest approach to the Sun, called the perihelion, shifts slightly with each orbit, in a way Newton's theory couldn't fully explain. The discrepancy was small, only 43 arc-seconds per century, but it was real and unexplained. When Einstein calculated Mercury's orbit using general relativity, he found that the curved space-time near the Sun naturally explained this excess precession. The announcement of this result, before his theory was even fully published, brought Einstein to tears of joy. For the first time, his radical new ideas about gravity had made a testable prediction that matched observations. It was a profound moment in the history of physics. Another early test came in 1919 during a solar eclipse. General relativity predicts that light passing near the Sun should be deflected by the Sun's gravitational field, or more accurately, by the curvature of space-time near the Sunday. The amount of deflection is twice what you would calculate using Newtonian physics if you treated light as particles affected by gravity. During the eclipse, astronomers could observe stars whose light passed close to the Sun, something normally impossible due to the Sun's brightness. The British astronomer Arthur Eddington led expeditions to Brazil and West Africa to photograph stars during the eclipse. When the results were analysed, they showed that starlight was indeed deflected by approximately the amount Einstein's theory predicted. The announcement made Einstein an international celebrity overnight. Newspapers around the world proclaimed that space was curved, that Newton had been overthrown, that a new understanding of the universe had emerged. While the 1919 measurements weren't as precise as later experiments would be, they represented a crucial turning point. General relativity was no longer just an elegant mathematical theory. It was a description of physical reality. Since then, countless experiments have tested general relativity in increasingly precise ways, and it has passed every test. We've measured gravitational time dilation using atomic clocks on airplanes and satellites. We've observed the bending of light by galaxies and galaxy clusters, an effect called gravitational lensing. We've detected gravitational waves, ripples in space-time itself produced by accelerating masses, exactly as Einstein's theory predicts. But it's in strong gravitational fields that general relativity truly distinguishes itself from Newtonian gravity. Near a black hole, the curvature of space-time becomes so extreme that Newtonian physics completely breaks down. Time doesn't just run slower, it approaches a standstill at the event horizon. Light doesn't just bend slightly, it can orbit the black hole or be captured entirely. The very notion of space and time as separate entities becomes problematic. Understanding this requires thinking in terms of space-time diagrams, a powerful tool developed to visualize the structure of space-time. In such a diagram, we typically plot time on the vertical axis and space on the horizontal axis. The path of an object through space-time, called its world line, is represented as a curve on the diagram. In flat space-time, far from any massive objects, world lines are straight. Light travels at a 45-degree angle on the diagram, the maximum slope representing the speed limit of the universe. Massive objects travel at less than the speed of light and have steeper world lines. Near a black hole, the geometry of these diagrams becomes distorted. As you approach the event horizon, the light cones, which represent the possible directions you can travel into the future, tip over. At the event horizon itself, the light cones tip over completely. The only possible future direction points toward the singularity at the center of the black hole. This is what it means for the event horizon to be a point of no return. It's not that some enormous force grabs you and won't let go. Rather, the geometry of space-time itself has become so warped that all future-pointing paths lead inward. Trying to escape a black hole after crossing the event horizon would be like trying to travel backward in time. The geometry simply doesn't permit it. Inside the event horizon, something even stranger happens. The roles of space and time exchange. The radial direction toward the singularity, which was a direction in space outside the horizon, becomes time-like inside. You can no more stop moving toward the singularity than you can stop time from flowing forward. Meanwhile, the time direction becomes space-like. In principle, you could move forward or backward in what used to be time, though this doesn't help you escape, because all directions in space now point toward your future, which includes the singularity. This exchange of roles between space and time is one of the most mind-bending features of black holes. It defies intuition because we have no everyday experience with such extreme space-time curvature. But it follows directly from the mathematics of general relativity, from Einstein's equations describing how matter and energy curve the fabric of the universe. At the very center of a black hole, the mathematics predicts a singularity, a point where space-time curvature becomes infinite and our equations break down entirely. Here, density becomes infinite, volume shrinks to zero, and the known laws of physics cease to apply. The singularity represents the ultimate limit of general relativity, a place where the theory predicts its own failure. Most physicists believe that the singularity isn't truly a point of infinite density, but rather a signal that we need a more complete theory, one that unifies general relativity with quantum mechanics. This hoped-for theory of quantum gravity would describe what happens at the singularity without requiring infinities. But we don't yet have such a theory, and in the absence of direct observational evidence from inside black holes, the true nature of the singularity remains one of the deepest mysteries in physics. Chapter 3: The Birth of Darkness. Black holes are born from death. To understand their formation, we need to understand the life cycle of stars. Stars are born when clouds of gas and dust in space collapse under their own gravity. As the cloud contracts, it heats up. Eventually, the core becomes hot and dense enough for nuclear fusion to begin. Hydrogen atoms fuse to form helium, releasing enormous amounts of energy in the process. This energy creates an outward pressure that balances the inward pull of gravity. The star reaches an equilibrium, a delicate balance between the crushing force of its own gravity and the explosive energy of nuclear fusion. Our Sun has been in this equilibrium state for about 4.6 billion years, and will remain there for another 5 billion years or so. But this balance can't last forever. Eventually, every star exhausts its nuclear fuel. When the hydrogen in the core runs out, fusion stops, pressure drops, and gravity begins to win. For stars like our Sun, the core contracts and heats up until it's hot enough to fuse helium into carbon and oxygen. The outer layers expand dramatically, and the star becomes a red giant, large and luminous, but with a cooler surface temperature. For relatively low-mass stars like the Sun, this is nearly the end of the story. The star puffs off its outer layers in a planetary nebula, leaving behind a hot, dense core called a white dwarf. This white dwarf, about the size of Earth but containing a significant fraction of the Sun's original mass, is supported against further collapse by electron degeneracy pressure, a quantum mechanical effect that arises from the Pauli exclusion principle. The Pauli exclusion principle states that no two electrons can occupy exactly the same quantum state. When you try to squeeze electrons into a small volume, they resist, creating a pressure that doesn't depend on temperature. This degeneracy pressure can support a white dwarf indefinitely, even as it slowly cools over trillions of years, eventually becoming a cold, dark black dwarf, though the universe isn't old enough yet for any black dwarfs to have formed. But there's a limit to how much mass electron degeneracy pressure can support. Chandrasekhar's calculation in 1930 showed that above about 1.4 solar masses, electron degeneracy pressure isn't strong enough. If a white dwarf somehow accumulates more mass, perhaps by pulling material from a companion star, it will collapse. This collapse can trigger a runaway fusion reaction that completely destroys the star in what's called a Type Ia supernova, one of the brightest events in the universe. For more massive stars, those born with more than about 8 times the Sun's mass, the story is quite different and much more dramatic. These stars have enough mass and internal pressure to fuse progressively heavier elements. After hydrogen is exhausted in the core, helium fusion begins, then carbon, neon, oxygen, and silicon, each burning at higher temperatures and for shorter periods. The star develops an onion-like structure, with shells of different elements burning at different depths. This process continues until the core starts producing iron. Iron is the most stable atomic nucleus. Unlike lighter elements, fusing iron doesn't release energy. Instead, it requires energy. When the core becomes primarily iron, fusion can no longer support the star against gravity. The core has reached the end of the line, and catastrophe is imminent. What happens next unfolds on a timescale of seconds, one of the fastest and most violent events in the universe. The iron core collapses under its own weight. As it collapses, several dramatic processes occur almost simultaneously. The intense heat causes iron nuclei to break apart into protons and neutrons, a process called photodisintegration that absorbs enormous energy. Electrons are forced to combine with protons to form neutrons, releasing a flood of neutrinos. The core collapses at speeds reaching 23% of the speed of light. The collapse continues until the core reaches nuclear densities, similar to the density inside an atomic nucleus. At this point, the strong nuclear force, which causes protons and neutrons to repel each other at very short distances, suddenly provides resistance. The collapse halts abruptly, and the core rebounds like a compressed spring suddenly released. This rebound generates a powerful shockwave that propagates outward through the star. Meanwhile, the flood of neutrinos produced during the collapse carries away an enormous amount of energy, about 99% of the total energy released in the collapse. Some of these neutrinos are absorbed by the material behind the shockwave, heating it and helping drive the explosion. The shockwave, strengthened by neutrino heating and other complex physics still not fully understood, blows the outer layers of the star into space at speeds of thousands of kilometers per second. This explosion is a core collapse supernova, specifically a Type II supernova, one of the most luminous events in the universe. For a few weeks, a single supernova can outshine an entire galaxy of hundreds of billions of stars. The explosion scatters the star's outer layers into space, enriching the interstellar medium with heavy elements forged in the star and in the explosion itself. Much of the carbon, oxygen, iron, and other elements that make up planets and living things, including the atoms in your body, were created in supernovae billions of years ago. But what about the core? If the collapsed core has a mass below about 2 to 3 solar masses, neutron degeneracy pressure and the strong nuclear force can support it against further collapse, the result is a neutron star, one of the densest forms of matter in the universe. A neutron star might be only 20 kilometers across, about the size of a city, yet contain more mass than the Sunday. A teaspoon of neutron star material would weigh about 1 billion tons on Earth. Neutron stars are remarkable objects in their own right. Many are pulsars, rapidly spinning neutron stars that emit beams of radiation from their magnetic poles. As the star rotates, these beams sweep across space like lighthouse beams, and if Earth happens to lie in the path, we detect regular pulses of radiation, sometimes many times per second. But if the collapsed core is more massive than the maximum mass a neutron star can support, somewhere between 2 and 3 solar masses, depending on the exact properties of matter at nuclear densities, then even neutron degeneracy pressure and the strong nuclear force aren't enough. Nothing in the known laws of physics can halt the collapse. The core continues to shrink, compressing to smaller and smaller sizes as gravity overwhelms all resistance. As the core shrinks below its Schwarzschild radius, an event horizon forms. The collapse doesn't stop there. According to general relativity, the collapse continues inexorably inward until all the mass is compressed into a singularity of infinite density and zero volume. The black hole has been born. This entire process, from the beginning of core collapse to the formation of a black hole, takes less than a second. It's almost incomprehensibly fast. A catastrophic transformation of a stellar core into a space-time singularity in the blink of an eye. Recent observations have revealed complexities in this picture. In some cases, the supernova explosion may be relatively weak, and a significant amount of material falls back onto the newly formed neutron star, pushing it over the mass limit and causing it to collapse into a black hole seconds or minutes after initially forming. In other cases, particularly for very massive stars, the core may collapse directly to a black hole without producing a bright supernova at all, a process sometimes called a failed supernova. The discovery in 2024 of a black hole triple system provided intriguing evidence for an alternative formation mechanism. In this system, a black hole orbits in a binary with one nearby star, while a second, much more distant star also orbits the pair. The fact that the distant star remains gravitationally bound suggests the black hole formed gently, without the violent kick that typically accompanies a supernova. This supports the idea of direct collapse, where a star's core caves in on itself without a dramatic explosion, simply sinking below its event horizon like an object disappearing beneath the surface of a dark pool. In November 2024, astronomers discovered LID 568, a black hole feeding at an extraordinary rate, consuming matter more than 40 times faster than the theoretical limit called the Eddington limit. This black hole, observed as it appeared just 1.5 billion years after the Big Bang, provides clues about how supermassive black holes grew so rapidly in the early universe, a puzzle that has long troubled astronomers. Not all stellar mass black holes form from single stars. When two neutron stars orbit each other closely, they gradually spiral inward, losing energy to gravitational waves. Eventually, they merge, creating either a more massive neutron star or, if the combined mass exceeds the neutron star limit, a black hole. The merger produces a brief burst of gravitational waves that can be detected by instruments like LIGO and Virgo, followed by a bright kilonova as heavy elements forged in the merger decay radioactively. In October and November 2024, gravitational wave detectors observed two remarkable mergers involving what appear to be second-generation black holes formed from previous mergers. These events showed unusual properties, including rapidly rotating black holes and spin directions opposite to their orbital motion, providing new insights into how black holes form and evolve in dense stellar environments. Chapter 4: The Point of No Return. The event horizon is the defining feature of a black hole, the boundary that separates the inside from the outside, the knowable from the unknowable. It's a one-way membrane in space-time. Things can cross it going in, but nothing can come back out. Not matter, not light, not information of any kind. But what exactly is the event horizon? It's crucial to understand that it's not a physical surface or barrier. There's no wall, no membrane, nothing you could touch or bounce off. It's purely a geometric feature of space-time, a place where the curvature becomes so extreme that all future-pointing paths lead inward. For a non-rotating black hole, the event horizon is a perfect sphere surrounding the singularity. Its size is determined by the black hole's mass through a simple relationship discovered by Schwarzschild. The Schwarzschild radius, as it's called, equals twice the gravitational constant times the mass, divided by the speed of light squared. For a black hole with the mass of our Sun, the Schwarzschild radius is about 3 kilometers. For Sagittarius A star, with over 4 million solar masses, it's about 12 million kilometers. Think about what this means. If you could somehow compress the Sun, which currently has a diameter of about 1.4 million kilometers, down to a sphere only 6 kilometers across, it would become a black hole. Every bit of the Sun's mass would still be there, but compressed into such a small volume that the space-time curvature at the surface would be extreme enough to trap light. Rotating black holes, which are more realistic since most stars rotate and angular momentum is conserved during collapse, have a more complex geometry described by the Kerr solution to Einstein's equations. A rotating black hole has two event horizons, an outer event horizon and an inner Cauchy horizon, and a region called the ergosphere, where space-time itself is dragged around by the black hole's rotation. The rotating black hole also has a smaller event horizon than a non-rotating black hole of the same mass. For a maximally rotating black hole, the event horizon radius can be as small as half the Schwarzschild radius. The rotation adds complications but doesn't change the fundamental property of the event horizon as a boundary of no return. What would you experience if you fell toward a black hole? The answer depends dramatically on your perspective. Let's imagine two scenarios. You're in a spaceship falling toward a black hole, and your friend is watching from a safe distance far away. From your perspective, falling toward the black hole, nothing particularly special happens as you cross the event horizon. You don't hit a wall. You don't feel a sudden jolt. If the black hole is large enough, you wouldn't even notice strong tidal forces yet. The event horizon isn't a place in the sense of being somewhere physically distinct. It's simply the point in space-time where your future becomes restricted to paths leading inward. You might look back and see the universe behind you behaving strangely. As you fall, light from the outside universe becomes blue-shifted to higher energies and frequencies in your forward direction. Behind you, light becomes increasingly red-shifted. The entire visible universe appears to compress into a shrinking circle behind you, while the region ahead darkens. But these are optical effects, not physical barriers. You pass through the event horizon and continue falling toward the singularity. However, from your friend's perspective, watching from far away, something very different happens. As you approach the event horizon, your friend sees you moving more and more slowly. Time dilation becomes extreme near the horizon. Your clock appears to run slower and slower compared to your friend's clock. The light from your spaceship becomes increasingly redshifted, shifted toward longer wavelengths and lower energies. Your spaceship appears to grow dimmer and redder. Asymptotically, it appears to approach the event horizon but never quite reaches it. Instead, your image freezes just above the horizon, growing ever dimmer and redder, eventually fading from view entirely as the light becomes too redshifted to detect. This dramatic difference in perspectives is a fundamental feature of relativity. What each observer measures depends on their frame of reference, their position and motion in space-time. Neither perspective is more correct than the other. They're simply different views of the same space-time events. This relativity of simultaneity becomes extreme near a black hole. Events that are simultaneous in one reference frame are not simultaneous in another. There's no universal present moment, no absolute now that all observers agree on. Your crossing of the event horizon happens at a definite moment in your own reference frame, but from your friend's external reference frame, that moment stretches out indefinitely into the future, never quite arriving. Near the event horizon, there's another important radius, called the photon sphere. This is the distance at which light can orbit the black hole in a circular path. At exactly 1.5 times the Schwarzschild radius for a non-rotating black hole, photons can travel in perfect circles around the black hole. These orbits are unstable. Any tiny perturbation sends the photon either falling into the black hole or escaping to infinity. The photon sphere has profound observational consequences. It's responsible for the dark shadow we see in black hole images. Light emitted just inside the photon sphere falls into the black hole. Light emitted just outside can escape. This creates a sharp boundary, the edge of the shadow, which appears larger than the event horizon itself due to various relativistic effects including gravitational lensing. When the Event Horizon Telescope imaged the supermassive black holes M87 star and Sagittarius A star, what they actually photographed wasn't the event horizon directly, which is fundamentally invisible, but rather this shadow, silhouetted against the bright glow of the accretion disk. The shadow appears about 2.6 times larger than the event horizon radius, a prediction of general relativity that the observations beautifully confirmed. For a stellar mass black hole, the tidal forces near the event horizon would be catastrophic. Tidal forces arise because gravity is stronger closer to the black hole. If you were falling in feet first, your feet would experience much stronger gravity than your head. This difference would stretch you along the radial direction while compressing you perpendicular to it, an effect colourfully termed spaghettification. For a stellar mass black hole of 10 solar masses, the tidal forces become lethal well before you reach the event horizon, likely ripping you apart when you're still thousands of kilometres away. But for a supermassive black hole like Sagittarius A star or M87 star, the event horizon is so large that the curvature, while extreme globally, is relatively gentle locally. The tidal forces at the horizon of a billion solar mass black hole would be no stronger than the tidal forces you experience on Earth from the Moon, completely survivable, at least momentarily. This seems paradoxical. How can crossing the ultimate boundary of the universe, the point beyond which nothing returns, be such an uneventful experience? The answer lies in the equivalence principle, one of Einstein's foundational insights. Locally, in a small region of space-time, you can't distinguish between being in a gravitational field and being in an accelerating reference frame. Freefall in a gravitational field is locally indistinguishable from floating in empty space far from any masses. When you cross the event horizon in freefall, you're following a geodesic, the straightest possible path through space-time. Locally, there's nothing to indicate you've crossed a special boundary. It's only globally, considering the entire structure of space-time, that the event horizon's special properties become apparent. Once you've crossed the event horizon, though, your fate is sealed. You will reach the singularity. There's no escape, not because any force prevents it, but because the geometry of space-time inside the horizon is such that all future-pointing paths lead to the singularity. Moving toward the singularity becomes as inevitable as moving forward in time. How long do you have? For a stellar mass black hole, the time from crossing the event horizon to reaching the singularity is extremely brief, typically microseconds. For a supermassive black hole, you might have hours or even days, depending on the mass. But regardless of the timeline, the endpoint is the same. As you approach the singularity, tidal forces grow without bound. Eventually, they become strong enough to tear apart molecules, then atoms, then even atomic nuclei. In the final moments, space-time itself becomes so violently curved that the very notion of matter as we understand it breaks down. You reach the singularity, and there the known laws of physics simply cease to apply. What happens at the singularity is one of the deepest mysteries in physics. General relativity predicts that curvature becomes infinite, that density becomes infinite, that all the matter that ever fell into the black hole is compressed into zero volume. But infinity isn't a number. It's a signal that our theory has reached its limits, that we need new physics to describe what really happens. Most physicists believe that quantum mechanics, the physics of the very small, must somehow modify the classical picture of the singularity. Perhaps there's a minimum possible volume set by quantum effects that prevents true infinite density. Perhaps the singularity is replaced by some kind of quantum structure we don't yet understand. But without a complete theory of quantum gravity, we can only speculate. The event horizon ensures that this uncertainty doesn't matter for the outside universe. Whatever happens at the singularity stays hidden behind the event horizon. This is sometimes called cosmic censorship, the idea that nature hides singularities from view, preventing them from affecting the rest of the universe. While not proven for all possible situations, cosmic censorship seems to hold in all physically realistic scenarios we've analyzed. Chapter 5: The Gravitational Symphony. In September 2015, a pair of detectors in Louisiana and Washington state detected something extraordinary. A slight ripple in space-time itself, a wave of gravitational distortion that stretched and compressed the very fabric of space by less than the width of a proton. This signal, lasting only a fraction of a second, carried a message from 1.3 billion light-years away. Two black holes had merged. This was the first direct detection of gravitational waves, confirming a century-old prediction by Einstein and opening an entirely new way of observing the universe. The merging black holes, with masses of about 36 and 29 solar masses respectively, had spiraled together over millions or billions of years, gradually losing energy to gravitational wave emission. In the final moments, they orbited each other hundreds of times per second before merging into a single black hole of about 62 solar masses. The missing 3 solar masses, about as much mass as 3 suns, was converted into energy and radiated away as gravitational waves, according to Einstein's equation, E equals mc squared. The peak power output during the final moments of the merger was about 50 times greater than the combined light output of all the stars in the observable universe. For that brief instant, Those two colliding black holes were the most luminous event in the universe, though they emitted no light at all, only gravitational waves. Gravitational waves are fundamentally different from electromagnetic waves like light. While light is a disturbance in electromagnetic fields, gravitational waves are disturbances in space-time itself. They're ripples in the fabric of reality, causing distances to alternately stretch and compress as they pass. A gravitational wave traveling through your body would make you alternately slightly taller and slightly wider, then slightly shorter and slightly narrower, oscillating at the frequency of the wave. The effect is incredibly subtle. Even the powerful gravitational waves from merging black holes cause displacements of only about 1 part in 10 to the 21st. The LIGO detectors, which use laser interferometry to measure changes in the distance between mirrors 4 kilometers apart, must be sensitive enough to detect changes in distance smaller than the diameter of a proton. This requires extraordinary engineering, accounting for seismic noise, thermal noise, quantum noise, and countless other potential sources of interference. Since that first detection in September 2015, LIGO and its European counterpart Virgo have detected dozens of black hole mergers, along with neutron star mergers and mixed systems involving both black holes and neutron stars. Each detection provides new information about the population of black holes, their masses, spins, and formation mechanisms. The gravitational wave signal from a black hole merger has a characteristic shape called a chirp. As the black holes spiral closer together, they orbit faster and faster, producing gravitational waves of increasing frequency and amplitude. This creates a rising tone, like a bird's chirp. By analyzing the exact shape of the chirp, scientists can determine the masses of the merging black holes, their spins, their distance from Earth, and even test whether the merger proceeds according to general relativity or requires modifications. So far, every merger has matched general relativity's predictions with remarkable precision. The theory, formulated over a century ago based on thought experiments and philosophical principles, correctly describes the collision of black holes with masses tens of times that of the Sun, releasing more energy than all the stars in the visible universe combined. This is one of the great triumphs of theoretical physics. Some mergers have revealed surprising features. Many of the black holes detected by LIGO are more massive than expected based on observations of stellar mass black holes in our galaxy. Some appear to be second-generation black holes formed from previous mergers. The spins of merging black holes sometimes point in unexpected directions, suggesting complex formation scenarios in dense stellar environments. In May 2023, gravitational wave detectors observed a particularly intriguing signal, suggesting the collision between a black hole and a neutron star, where the neutron star might have been torn apart before being swallowed. Such events provide unique laboratories for studying matter under extreme conditions and potentially producing heavy elements through rapid neutron capture processes. Looking to the future, next-generation gravitational wave detectors are being planned. The Einstein Telescope in Europe and Cosmic Explorer in the United States will be far more sensitive than current detectors, capable of seeing black hole mergers throughout most of the observable universe. They'll detect thousands of mergers per year, providing a complete census of how black holes form, evolve, and merge across cosmic history. Space-based detectors like LISA, the Laser Interferometer Space Antenna, planned for launch in the 2030s, will detect gravitational waves at lower frequencies, opening a window on supermassive black hole mergers. When two galaxies collide and merge, their central black holes eventually sink to the center of the merged galaxy and coalesce. LISA will detect the gravitational waves from these cosmic collisions, observing events billions of light years away and billions of years in the past. These observations will help answer fundamental questions about how supermassive black holes grow. Did they start as stellar mass black holes that gradually accreted mass over billions of years? Or did they form through direct collapse of massive gas clouds in the early universe? How often do supermassive black holes merge? And what happens to galaxies when they do? Gravitational wave astronomy provides a way to observe black holes directly without relying on the light from surrounding matter. Chapter 6. The Engines of Quasars. In 1963, astronomer Martin Schmidt was studying a peculiar radio source called 3C 273. The object appeared star-like in optical images, but its spectrum was baffling, showing emission lines at wavelengths that didn't match any known elements. Then Schmidt had a breakthrough. The lines were familiar hydrogen lines, but enormously redshifted. If this redshift was due to cosmic expansion, the object had to be billions of light-years away. At such a distance, for 3C 273 to be visible at all, it had to be incredibly luminous, about 1 trillion times brighter than the Sun, outshining an entire galaxy of hundreds of billions of stars. Yet it was small, varying in brightness over periods of months. Since an object can't vary faster than light can travel across it, this meant 3C 273 could be no more than a few light months across, tiny compared to a galaxy, but producing vastly more energy. What could possibly generate such enormous power in such a small volume? The answer, scientists gradually realized, was a supermassive black hole actively feeding on surrounding matter. 3C 273 was the first clearly identified member of a class of objects called quasars, quasi-stellar radio sources, among the most energetic phenomena in the universe. We now understand quasars as the brilliant centers of distant galaxies, powered by supermassive black holes accreting matter at tremendous rates. As gas spirals into the black hole, it forms an accretion disk, where material orbits at speeds approaching the speed of light. Friction and magnetic forces heat the disk to temperatures of millions or billions of degrees, causing it to glow brilliantly across the electromagnetic spectrum from radio waves through visible light to X-rays and gamma rays. The energy generation is staggeringly efficient. A black hole accretion disk converts about 10% of infalling matter's rest mass into energy, compared to only about 0.7% for nuclear fusion in stars. This makes black hole accretion one of the most efficient energy generation mechanisms in the universe. A black hole consuming just a few solar masses per year can outshine an entire galaxy. But accretion disks are only part of the story. Many active black holes also produce jets, narrow beams of plasma ejected perpendicular to the accretion disk at speeds approaching the speed of light. These jets can extend for millions of light years, creating enormous lobes of radio emission far outside the host galaxy. The jet from M87's central black hole, for instance, extends about 5,000 light-years from the galactic center and shows features moving outward at apparent speeds faster than light. These apparent superluminal motions aren't violations of relativity. They're optical illusions created when a jet moving at nearly the speed of light is pointed almost directly at us. Material in the jet is moving almost as fast as the light it emits, so light emitted at different times arrives at Earth with only small time differences, making the motion appear compressed and faster than light. How jets are launched remains an active area of research. The leading theory involves magnetic fields threading the accretion disk and the black hole itself. As the disk rotates, it twists magnetic field lines, which extract rotational energy from the disk or from the spinning black hole itself and redirect it into the jet. This Blandford-Znajek mechanism, named after physicists Roger Blandford and Roman Znajek, who proposed it in 1977, can tap the rotational energy of a spinning black hole, converting it into kinetic energy in the jet. The jets interact with their surroundings in dramatic ways. As they plow through intergalactic gas, they create shock waves and heat the gas, sometimes preventing it from cooling and forming stars. This feedback from active galactic nuclei appears to play a crucial role in galaxy evolution, helping explain why the most massive galaxies have surprisingly little ongoing star formation. The black hole at their center, through its jets and winds, has heated the surrounding gas enough to prevent star formation, essentially turning off the galaxy's ability to grow. The relationship between black holes and their host galaxies is one of the most intriguing discoveries in modern astrophysics. Astronomers have found that the mass of a galaxy's central black hole correlates tightly with properties of the galaxy's bulge. The central concentration of stars, a galaxy with a more massive bulge, has a more massive black hole, with the black hole typically containing about 0.1% of the bulge mass. This correlation is remarkable because the black hole, despite its enormous mass, influences only a tiny region at the galaxy's center. The bulge extends thousands of light years, while the black hole's sphere of influence extends only a few light years at most. Yet somehow, these two components seem to know about each other, growing together over cosmic time. The most likely explanation involves feedback. When a black hole actively accretes and produces jets or winds, it heats the surrounding gas, preventing infall. This regulates the black hole's own growth and affects star formation throughout the galaxy. Over billions of years, this mutual interaction leads to the observed correlation. The black hole and galaxy co-evolve, each shaping the other's development. Quasars were much more common in the early universe than they are today. Looking back through cosmic time by observing very distant objects, astronomers see that the quasar population peaked about 10 billion years ago, when the universe was about a quarter of its current age. Since then, quasar activity has declined dramatically. Most supermassive black holes in the present-day universe, including our own Sagittarius A star, are relatively quiet, accreting at very low rates. This evolution reflects the cosmic history of galaxy mergers. In the early universe, galaxies were smaller and collided more frequently. These collisions funneled gas towards central black holes, triggering intense accretion and quasar activity. As the universe expanded and galaxies became more spread out, major mergers became less common. Additionally, many galaxies exhausted their central gas supplies, leaving their black holes starved for fuel. Some quasars are so distant that we see them as they existed less than a billion years after the Big Bang. These early quasars contain black holes of 1 billion solar masses or more, raising a puzzle. How did such massive black holes form so quickly? The universe wasn't old enough for a stellar mass black hole to grow to supermassive size through steady accretion, even at the maximum possible rate. This suggests that supermassive black holes might form through alternative mechanisms. Perhaps massive black hole seeds formed directly from the collapse of enormous gas clouds in the early universe. Perhaps stellar collisions in dense star clusters built supermassive stars that collapsed to black holes. Perhaps black holes grew through super-Eddington accretion, consuming matter faster than standard theory allows. The discovery of LID 568 inches November 2024, feeding at over 40 times the Eddington limit, provides direct evidence that such super-Eddington accretion is possible. Chapter 7. When black holes collide. Galaxy collisions are among the most dramatic events in the cosmos. Despite the name, galaxies don't collide like billiard balls. They're mostly empty space, so individual stars rarely collide. Instead, the galaxies pass through each other, their gravitational fields interacting in complex ways that distort their shapes and alter their trajectories. Often, two colliding galaxies will eventually merge, forming a single larger galaxy. This process takes hundreds of millions to billions of years, with multiple passes as the galaxies spiral around their common center of mass, shedding energy through dynamical friction until they finally coalesce. When galaxies merge, so do their central black holes, though this process is more complicated than you might expect. Initially, the two black holes are far apart, each at the center of its original galaxy. As the galaxies merge, the black holes sink toward the center of the merged galaxy through dynamical friction, interactions with stars and gas clouds that gradually rob them of energy and angular momentum. Eventually, the black holes get close enough to form a bound binary system, orbiting each other. At this point, dynamical friction becomes ineffective because the black holes are moving too fast through a region that's been largely cleared of stars and gas. The binary enters what's called the final parsec problem. How does it shrink from a separation of about 1 parsec, roughly 3 light-years, down to the tiny distances where gravitational wave emission becomes efficient? Several mechanisms might solve this problem. Interactions with stars on particular orbits can extract energy from the binary. Gas accretion, if both black holes are feeding simultaneously, can also remove energy. In dense stellar environments like galactic nuclei, three-body interactions where a star passes close to the binary can carry away energy. Once the black hole separation shrinks below about a light-year for typical supermassive black holes, gravitational wave emission takes over. The binary begins radiating significant gravitational wave energy, causing the orbit to shrink faster and faster in an accelerating spiral. In the final stages, the black holes orbit each other thousands of times per second, producing gravitational waves of increasing frequency and amplitude, the characteristic chirp signal we discussed earlier. The merger itself is extraordinarily energetic. A typical supermassive black hole merger releases about 1 solar mass worth of energy in gravitational waves over the final seconds. For the most massive mergers, total energy output can reach hundreds of solar masses. This energy, released almost instantaneously, creates some of the most powerful events in the universe since the Big Bang. The merged black hole that results is still ringing from the collision, oscillating like a struck bell in various modes. These ring-down oscillations, predicted by general relativity, radiate away over milliseconds to seconds, carrying information about the final black hole's mass and spin. By analyzing the ring-down signal, scientists can test whether the final object is indeed a black hole, as general relativity predicts, or some exotic alternative. The gravitational waves from supermassive black hole mergers carry energy and momentum, and if the emission is asymmetric, they can give the merged black hole a kick, propelling it away from the center of the merged galaxy at speeds up to thousands of kilometers per second. Some kicked black holes might escape their host galaxy entirely, wandering through intergalactic space, while others eventually settle back to the galactic center after millions of years. Evidence for these recoiling black holes comes from observations of quasars with unusual properties, offset from their galaxy centers or showing multiple sets of emission lines, suggesting 2 separate black holes not yet merged. In some cases, astronomers have found galaxies with off-center bright nuclei, possibly indicating a recoiling black hole that's still accreting gas as it moves through the galaxy. Our own Milky Way provides a future laboratory for studying black hole mergers. In about 4 to 5 billion years, the Milky Way will collide with the Andromeda Galaxy, our nearest large galactic neighbor. Both galaxies contain supermassive black holes at their centers. Sagittarius A star in the Milky Way with about 4 million solar masses, and Andromeda's black hole with perhaps 10 times that mass. As the galaxies merge, these black holes will sink toward the center of the merged galaxy, eventually forming a binary and then merging into a single black hole containing perhaps 50 million solar masses. This merger will produce gravitational waves detectable by space-based detectors like LISA, though of course we won't be around to observe it. By then, our Sun will have evolved into a red giant and possibly engulfed Earth. The effect on solar systems in the merging galaxies is interesting to contemplate. Despite the dramatic nature of galaxy mergers, individual stars rarely collide because the distances between stars are so vast compared to stellar sizes. Our solar system would likely survive the Milky Way-Andromeda collision, though our orbit around the galactic center might be significantly altered. We might end up farther from or closer to the center of the merged galaxy, which will likely be an elliptical galaxy dubbed Milkomeda. Chapter 8. The Quantum Mystery. Black holes exist at the intersection of two great theories of 20th century physics: general relativity, which describes gravity and space-time curvature, and quantum mechanics, which describes the behavior of matter and energy at the smallest scales. These theories are phenomenally successful within their domains, but appear fundamentally incompatible. General relativity is deterministic and continuous. It describes space-time as a smooth, curved manifold where events unfold with certainty. Quantum mechanics is probabilistic and discrete. It describes a world of uncertainty, where particles exist in superpositions of states until measured, where energy comes in discrete packets, where the very act of observation affects what is observed. Most of the time, this incompatibility doesn't matter. General relativity applies to massive objects and large scales where quantum effects are negligible. Quantum mechanics applies to tiny objects where space-time curvature is negligible. The two theories operate in different regimes and never directly conflict, except at black hole singularities. There, space-time curvature becomes infinite, quantum effects become crucial, and both theories are needed simultaneously. But we don't have a theory that unifies them. This is the problem of quantum gravity, one of the deepest unsolved problems in theoretical physics. The first hint that quantum mechanics might modify the classical picture of black holes came from Stephen Hawking in 1974. Hawking analyzed quantum field theory in the curved space-time around a black hole and made a startling discovery. Black holes aren't completely black, they radiate. Hawking radiation arises from quantum fluctuations in the vacuum near the event horizon. Even in empty space, quantum mechanics allows particle-antiparticle pairs to spontaneously appear and annihilate, borrowing energy from the vacuum for brief moments allowed by Heisenberg's uncertainty principle. Usually, these virtual particles appear and disappear so quickly that they have no observable effect. But near an event horizon, something different can happen. If a virtual particle pair appears just outside the horizon, one particle might fall into the black hole, while the other escapes to infinity. To an outside observer, it appears that the black hole has emitted a particle. The energy for this real particle comes from the black hole's mass, so the black hole slowly loses mass through this process. The temperature of Hawking radiation is inversely proportional to the black hole's mass. For stellar mass black holes, the temperature is incredibly low, about 1/10,000,000th of a degree above absolute zero, far colder than the cosmic microwave background. For supermassive black holes, it's even lower. These black holes are actually absorbing more energy from the cosmic microwave background than they emit through Hawking radiation, so they're growing, not shrinking. But as a black hole radiates, it loses mass, which increases its temperature, which increases its radiation rate. This creates a runaway feedback process. Eventually, after an unimaginably long time, the black hole evaporates completely in a final burst of high-energy radiation. For a solar mass black hole, The evaporation time is about 10 to the 67th power years. For comparison, the current age of the universe is only about 10 to the 10th power years. So, Hawking radiation is utterly negligible on human timescales or even on cosmological timescales. But it's profoundly important conceptually because it suggests that black holes aren't eternal. Hawking radiation also creates a paradox that has troubled physicists for decades. Quantum mechanics requires that information be conserved. If you know the complete quantum state of a system at one time, you can in principle calculate its state at any other time. Information can be scrambled or hidden but never truly destroyed. But if a black hole evaporates completely, what happens to the information about everything that fell in? The Hawking radiation appears to be completely thermal, containing no information about what created the black hole or what fell into it. This seems to violate quantum mechanics. This is the black hole information paradox. Various solutions have been proposed. Perhaps the information is encoded in subtle correlations in the Hawking radiation that we haven't properly accounted for. Perhaps it's preserved in a remnant left behind after the black hole mostly evaporates. Perhaps information is fundamentally destroyed in black holes, requiring a modification to quantum mechanics. Perhaps the paradox is resolved by quantum gravity in ways we don't yet understand. Recent work using the AD-CFT correspondence, a mathematical relationship between gravity in certain curved spacetimes, and quantum field theories without gravity, has provided new insights. These calculations suggest that information does escape in the Hawking radiation, but in such a scrambled form that it's practically impossible to reconstruct what fell in. The radiation remains essentially thermal for most of the evaporation process, with information only becoming accessible near the end. Another quantum mystery involves the structure of the event horizon itself. In classical general relativity, the horizon is completely featureless, a smooth boundary with no special properties other than being a point of no return. But quantum mechanics might change this picture. Some theories suggest that the horizon might have fine structure at quantum scales, perhaps a fuzzy region where quantum effects prevent a sharp boundary. Others propose that the horizon might be a firewall, a region of intense radiation that would destroy anything trying to cross it, contradicting the classical prediction that you could cross smoothly in free fall. The firewall paradox arises from trying to reconcile several seemingly incompatible requirements: that Hawking radiation be thermal and carry away information, that an observer crossing the horizon experiences nothing special, and that quantum mechanics be preserved. Different approaches to the paradox lead to different conclusions about what the horizon really is. These quantum mysteries won't be resolved without a complete theory of quantum gravity. String theory, loop quantum gravity, and other approaches all make different predictions about what happens at black hole singularities and horizons. But without direct observational evidence, we can't determine which, if any, is correct. Black holes might eventually provide tests of quantum gravity. The ring-down oscillations of merged black holes, if measured with sufficient precision, might reveal deviations from classical general relativity. The shadows of black holes, if imaged with even better resolution than the Event Horizon Telescope achieves, might show features indicating quantum structure at the horizon. Primordial black holes, if they exist, and some are light enough, might be detectable through their Hawking radiation. Chapter 9. Supermassive Mysteries. At the center of nearly every large galaxy lurks a supermassive black hole. Our Milky Way has Sagittarius A star. The giant elliptical galaxy M87 has a black hole of about 6.5 billion solar masses. The quasar TON 618, one of the most massive known, contains about 66 billion solar masses. How did these monsters form? This remains one of the major unsolved puzzles in astrophysics. We can observe supermassive black holes throughout the universe, from relatively nearby examples like Sagittarius A star to quasars in the early universe when it was less than 1 billion years old. But the path from stellar mass black holes to supermassive ones isn't clear. One possibility is steady growth through accretion. A black hole consuming gas from its surroundings can grow over time, but there's a limit to how fast this can occur, called the Eddington limit. As matter falls toward a black hole and heats up in the accretion disk, it radiates intensely. This radiation exerts outward pressure on surrounding gas, potentially preventing more material from falling in. The Eddington limit represents the balance point where radiation pressure equals gravitational attraction. For a solar mass object, the Eddington luminosity is about 30,000 times the Sun's luminosity. A black hole accreting at the Eddington limit and converting about 10% of infalling mass to energy would gain mass at about 1 solar mass every 30 million years. Starting from a 10 solar mass stellar black hole formed shortly after the Big Bang, accreting continuously at the Eddington limit for 13.8 billion years would produce a black hole of only about 10,000 solar masses. To reach 1 billion solar masses in less than 1 billion years requires either much faster accretion or a much larger starting seed. Super Eddington accretion, where the black hole feeds faster than the theoretical limit, might solve this problem. The discovery of LID 568 inches, November 2024, demonstrated that such rapid feeding is possible, at least temporarily. This black hole is consuming matter at over 40 times the Eddington rate, possibly during a brief phase of rapid growth following its formation. Another possibility involves starting with larger seeds. Instead of stellar mass black holes, perhaps supermassive black holes formed from direct collapse of massive gas clouds in the early universe. Under certain conditions, if the gas is very hot and metal poor, it might not fragment into stars, but instead collapse directly to form an intermediate mass black hole of thousands or hundreds of thousands of solar masses. These direct collapse black holes would have a head start, requiring less time to grow to supermassive sizes through normal accretion. Computer simulations have shown that such direct collapse is possible under the right conditions, which might have existed in some regions of the early universe. A third possibility involves dense star clusters. In the cores of young galaxies, stars might collide and merge, building up increasingly massive stars. There's a theoretical limit to how massive a star can be, around 150 to 300 solar masses, above which it becomes unstable. But in the extreme environment of the early universe, even more massive objects might form through stellar collisions. When these supermassive stars collapsed, they would form intermediate mass black holes that could serve as seeds for supermassive black holes. Alternatively, the dense stellar clusters themselves might undergo runaway collapse, with many stars and stellar black holes merging to form a single large black hole. The truth likely involves multiple formation pathways. Some supermassive black holes might have grown from stellar mass seeds through super Eddington accretion. Others might have started from direct collapse black holes. Still, others might have formed through stellar collisions and mergers. Different formation mechanisms might dominate at different times in cosmic history or in different environments. Black hole mergers also contribute to growth. When two galaxies merge, their central black holes eventually merge, creating a single, more massive black hole. Over cosmic time, through multiple mergers, black holes can grow substantially. The merger history of galaxies directly affects the mass distribution of supermassive black holes we observe today. Recent surveys have mapped the supermassive black hole population across cosmic time. By observing quasars and active galactic nuclei at different distances, and therefore different times in the past due to light's travel time, astronomers can reconstruct how the black hole population has evolved. The results show that black hole growth peaked about 10 billion years ago, roughly the same time that star formation peaked in the universe. Since then, both star formation and black hole growth have declined dramatically. This isn't a coincidence. Black holes and galaxies grow together, feeding from the same gas supplies and influencing each other's evolution. The relationship between black holes and dark matter adds another layer of complexity. Dark matter, which makes up about 85% of all matter in the universe, doesn't emit, absorb, or reflect light. We detect it only through its gravitational effects. Dark matter halos surround galaxies, providing the gravitational scaffolding that holds them together. Theory predicts that dark matter should form dense cusps at galaxy centers. Such cusps might affect black hole formation and growth, either by funneling more matter toward the center or by perturbing stellar orbits near the black hole. Some models even suggest that dark matter annihilation near black holes might produce detectable signals, though searches so far have found nothing definitive. There's also speculation about whether primordial black holes, hypothetical black holes formed in the very early universe from quantum fluctuations, might contribute to dark matter. Current constraints from various observations limit how much of dark matter could be in primordial black holes, but they haven't been completely ruled out. Chapter 10: The Extreme Physics Laboratory. Black holes represent the most extreme physical conditions accessible to observation, making them natural laboratories for testing fundamental physics. Near the event horizon, gravity is enormously strong, space-time curvature is extreme, and various relativistic effects become dramatic. This allows tests of general relativity that are impossible anywhere else. One crucial test involves the black hole shadow. General relativity makes specific predictions about the size and shape of this shadow based on the black hole's mass and spin. The Event Horizon Telescope observations of M87 star and Sagittarius A star confirmed these predictions, but with measurement uncertainties of about 20%, leaving room for small deviations. Alternative theories of gravity often predict different shadow sizes or shapes. By measuring the shadow more precisely, perhaps with future space-based very long baseline interferometry arrays, we could constrain or rule out various modified gravity theories. Any deviation from general relativity's predictions would be revolutionary, pointing toward new physics. Another test involves gravitational wave observations. The in-spiral, merger, and ring down of binary black holes occur exactly as general relativity predicts, with the waveform shape determined by the masses and spins of the merging black holes. By measuring these waveforms precisely, we can test whether the merger dynamics match Einstein's equations. So far, all observed mergers have been consistent with general relativity. The strain amplitude, frequency evolution, and ring-down frequencies all match predictions, but future detectors with better sensitivity might reveal small deviations, especially in the ring-down phase, where the merged black hole's oscillations could reveal departures from the classical picture if quantum effects or other new physics become important. Tests can also come from observing stars in close orbits around black holes. The star S2, orbiting Sagittarius A star with a 16-year period, passes within about 17 light-hours of the black hole at closest approach, traveling at about 2.5% of light speed. Observations during its 2018 closest approach detected gravitational redshift exactly as general relativity predicts. Future observations of S2 and other stars on even tighter orbits will measure additional relativistic effects. The orbit should precess, with the point of closest approach slowly rotating around the black hole due to both general relativistic effects and perturbations from other masses. The rate of precession depends on the black hole's spin through the Lense-Thirring effect, where rotating masses drag space-time around with them. By measuring orbital precession precisely, astronomers hope to determine not just that Sagittarius A star is spinning, but how fast it's spinning and in what direction. This would provide information about how the black hole formed and how it has accreted matter over its history. Even more extreme tests might come from observing hotspots in the accretion disk very close to the event horizon. These hotspots orbit the black hole at nearly light speed, experiencing extreme time dilation, gravitational redshift, and Doppler effects. Their observed properties depend sensitively on the exact structure of space-time near the horizon. With sufficiently detailed observations, perhaps creating movies of the accretion flow around black holes, we could map the space-time geometry in unprecedented detail and search for any deviations from general relativity. The hotspots could reveal whether the photon orbit and innermost stable circular orbit have the sizes and properties that general relativity predicts. Black holes also allow tests of quantum mechanics and the interplay between quantum theory and gravity. While Hawking radiation is too faint to detect from astrophysical black holes, we might find other signatures of quantum effects. If black holes have microscopic structure that we don't yet understand, it might affect observable properties in subtle ways. The information paradox, while primarily a theoretical concern, might eventually have observational consequences. If information does escape from black holes in ways beyond standard Hawking radiation, there might be subtle correlations in the radiation or other signatures that could be detected, at least in principle. Primordial black holes, if they exist with masses low enough for Hawking radiation to be significant, could provide more direct tests. A primordial black hole of about 10 to the 11th kilograms would have a Hawking temperature around room temperature and would be evaporating rapidly in the present-day universe. The radiation from such an evaporating black hole would have a distinctive spectrum that could distinguish it from other sources. Searches for evaporating primordial black holes have so far found nothing, which places constraints on how many low-mass primordial black holes can exist. But these searches continue, and a detection would be extraordinary, providing the first direct observation of Hawking radiation and quantum effects in black holes. Black holes might also serve as particle accelerators more powerful than anything we can build on Earth. When matter falls toward a black hole, it can reach enormous energies. Collisions between particles in the inner accretion disk or near the event horizon occur at energies far beyond what the Large Hadron Collider can achieve. These ultra-high energy collisions might produce exotic particles or phenomena that don't occur at lower energies. While we can't directly observe what happens in the accretion disk, we can observe the radiation it emits and search for signatures of new physics. Some theories predict that extra dimensions of space, microscopic black holes, or other exotic phenomena might become important at high energies and could leave detectable signatures in the radiation from accreting black holes. Chapter 11: The Information Paradox. The black hole information paradox represents one of the deepest conflicts in modern physics, a clash between two of our most successful theories that has occupied brilliant minds for nearly 50 years. At its heart lies a simple question with profound implications. What happens to information that falls into a black hole? In quantum mechanics, information is sacred. The fundamental laws are time reversible, meaning that if you know the complete quantum state of a system at any moment, you can, in principle, calculate its state at any other moment, past or future. Information might become scrambled, spread out, or hidden, but it can never be truly destroyed. This principle, called unitarity, is a cornerstone of quantum theory. But black holes seem to violate this principle. When something falls past the event horizon, all information about it appears to be lost to the outside universe. The black hole's external appearance is determined entirely by just three properties: its mass, spin, and electric charge. This is sometimes summarized by saying black holes have no hair, a phrase coined by John Wheeler. All other details about what fell in, its composition, structure, history, everything, seemed to disappear. Initially, this wasn't considered a serious problem. The information isn't destroyed, physicists reasoned. It's just hidden behind the event horizon, still existing inside the black hole. But then Hawking discovered that black holes radiate and eventually evaporate. If a black hole completely evaporates, the information inside would seem to vanish from the universe entirely. Hawking's calculation in 1974 showed that the radiation emitted by a black hole is purely thermal, depending only on the black hole's mass. Thermal radiation is maximally random, containing no information beyond its temperature. If this is correct, then the information about everything that fell into the black hole is lost when it evaporates, violating quantum mechanics. This triggered a fierce debate that continues today. Hawking initially argued that information really is destroyed in black holes, that quantum mechanics needs to be modified to allow information loss. This was a radical position, challenging one of the most fundamental principles in physics. Others sought ways to preserve information. Perhaps it escapes in the Hawking radiation through subtle correlations that Hawking's calculation missed. Perhaps it's stored in a tiny remnant left behind after the black hole mostly evaporates. Perhaps the information somehow leaks out through effects not captured by semi-classical calculations that treat gravity classically while treating matter quantum mechanically. One proposal that gained attention is the holographic principle, which suggests that all the information in a volume of space can be encoded on its boundary, like a hologram that stores three-dimensional information on a two-dimensional surface. Applied to black holes, this suggests that information about everything that fell in might be encoded on the event horizon itself. The holographic principle emerged from theoretical studies of black hole entropy. In the 1970s, Jacob Bekenstein and Stephen Hawking showed that black holes have entropy proportional to the area of their event horizon, not their volume. A black hole with twice the radius has 4 times the entropy. This area-entropy relationship hints at something profound about the nature of black holes and information storage. In string theory, attempts to explain this entropy microscopically led to the realization that a black hole's event horizon might have an enormous number of quantum states, with the entropy counting these states. This suggests the horizon has structure at quantum scales, though what this structure is remains unclear. The AD-CFT correspondence, discovered by Juan Maldacena in 1997, provided new mathematical tools for studying black holes. This correspondence is a duality between theories of gravity in certain curved spacetimes, called anti-de Sitter spaces, and quantum field theories without gravity living on the boundary of those spaces. While our universe isn't an ADS space, the correspondence has proven invaluable for understanding quantum aspects of gravity. Using AD-CFT, physicists have made progress on the information paradox. Calculations suggest that information does escape in Hawking radiation through subtle quantum correlations that develop between early and late radiation. The radiation starts out apparently thermal and uncorrelated with previous emissions, but as the black hole shrinks, correlations build up. By the time the black hole has mostly evaporated, the information is encoded in these correlations, though in such a scrambled form that reconstructing what fell in would be practically impossible. This resolution came from studying what's called the Page curve, named after physicist Don Page. The Page curve describes how the entropy of Hawking radiation should evolve over time if information is conserved. Initially, entropy increases as apparently random thermal radiation is emitted, but halfway through evaporation, entropy should start decreasing as the radiation becomes more correlated, returning to zero when evaporation completes. Recent calculations using quantum extremal surfaces, a generalization of classical horizons that includes quantum corrections, have reproduced the Page curve. This suggests that information is indeed conserved, consistent with quantum mechanics. When Stephen Hawking died in 2018, many physicists believed he would have ultimately accepted that information is not destroyed, though he never publicly conceded the point. But challenges remain. The firewall paradox, proposed in 2012 by physicists including Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully, pointed out tensions in the standard picture. If late Hawking radiation is correlated with early radiation to carry information, and also correlated with particles behind the horizon as quantum field theory requires, this leads to contradictions. Resolving this paradox might require even more radical changes to our understanding. Some proposals suggest the event horizon isn't smooth but contains a firewall of high-energy particles that would destroy anything trying to cross. This contradicts the equivalence principle, Einstein's insight that free fall in a gravitational field is locally indistinguishable from floating in empty space. Other proposals modify quantum mechanics in subtle ways or suggest that the interior of an evaporating black hole is more complex than classical general relativity indicates. The information paradox isn't just about black holes. It touches on fundamental questions about the nature of space-time, the relationship between gravity and quantum mechanics, and the ultimate laws governing our universe. A complete resolution will likely require a full theory of quantum gravity, still beyond our current reach. For now, the paradox remains at the frontier of theoretical physics, driving research and stimulating new ideas. It reminds us that despite our remarkable progress, we still don't fully understand the quantum nature of space-time or what happens in the most extreme gravitational environments. Chapter 12: Wormholes and Time Machines. Black holes have captured popular imagination not just for what they are, but for what they might enable. Science fiction is filled with stories of black holes as portals to other regions of space or even other times. While most such stories are pure fantasy, the actual physics of black holes allows some intriguing, if highly speculative, possibilities. The possibility of wormholes, shortcuts through space-time, connecting distant regions, emerges from solutions to Einstein's equations. The simplest example involves the maximally extended Schwarzschild solution, which describes not just the exterior of a black hole and the region inside the event horizon, but also an additional exterior region connected through the interior. In this solution, the black hole interior connects two different exterior regions of space-time. You could imagine entering the black hole from one exterior region and emerging in another. This connecting bridge is a wormhole, also called an Einstein-Rosen bridge, after Albert Einstein and Nathan Rosen, who studied these solutions in 1935. However, such wormholes are traversable only in theory. The Einstein-Rosen bridge forms and then pinches off so quickly that nothing, not even light, can traverse it before the two sides disconnect. Any particle attempting to pass through would be crushed at the bridge's throat before reaching the other side. Moreover, the other exterior region in the maximally extended Schwarzschild solution isn't another part of our universe, but rather a completely separate space-time. It's not like finding a shortcut to another galaxy. It's more like discovering a connection to an entirely different universe. To create a traversable wormhole, one that you could actually travel through, requires keeping the throat open. This demands what physicists call exotic matter, matter with negative energy density. In ordinary matter, all forms of energy are positive, but quantum field theory allows negative energy densities in certain circumstances, though only in small quantities and under special conditions. Some solutions in general relativity describe traversable wormholes held open by exotic matter, the Casimir effect, where quantum fluctuations between closely spaced metal plates create a negative energy density, demonstrates that exotic matter isn't completely forbidden by physics. But creating enough exotic matter to stabilize a human traversable wormhole appears to be far beyond any foreseeable technology. Even if traversable wormholes could exist, they raise troubling paradoxes. If a wormhole connects two regions of space, and one end is moved at high speed while the other remains stationary, time dilation effects mean the two ends age at different rates. This could create a time machine, with one wormhole mouth existing at an earlier time than the other. Time machines create logical paradoxes. The most famous is the grandfather paradox. You travel back in time and prevent your grandparents from meeting, so you're never born, so you can't travel back in time, so your grandparents do meet, and so on. Such paradoxes have led most physicists to conclude that time travel to the past is probably impossible, though proving this rigorously has been challenging. Stephen Hawking proposed the chronology protection conjecture, suggesting that the laws of physics prevent the formation of closed, time-like curves, except possibly on microscopic scales. Whenever conditions arise that might permit time travel, quantum effects intervene to prevent it. While not proven, this conjecture seems to hold in all situations analyzed so far. Rotating black holes add additional exotic features. The Kerr solution describing a spinning black hole contains not just an event horizon but also an inner horizon and a region called the ergosphere, where space-time is dragged around so strongly that nothing can remain stationary relative to distant observers. The Kerr solution also contains a ring singularity rather than a point singularity, and if analyzed mathematically, it connects to other regions of space-time with bizarre properties, including regions with closed time-like curves allowing time travel, and regions where gravity becomes repulsive. However, these exotic regions are probably not physically real, but rather artifacts of extending the solution beyond its domain of validity. In reality, any real rotating black hole formed from stellar collapse wouldn't have these features. The interior would be filled with infalling matter and radiation that would modify the geometry, likely preventing the exotic inner structure from forming. Theoretical studies suggest that the inner horizon is unstable and would be replaced by a more conventional singularity. Another speculative idea involves black hole mining or black hole engines. The ergosphere of a rotating black hole contains energy that can theoretically be extracted through the Penrose process, named after Roger Penrose, who discovered it in 1969. By dropping an object into the ergosphere in just the right way, you can have it split into two pieces, one falling into the black hole and one escaping with more energy than the original object. This process extracts rotational energy from the black hole, slowing its spin. For a maximally rotating black hole, up to 29% of its mass energy could theoretically be extracted this way. An advanced civilization might harness this energy, using a black hole as a power source. Some have even speculated about using black holes for computation. The extreme time dilation near a black hole means that a computer falling toward the horizon could perform an enormous number of calculations in what appears to outside observers as a brief time. There are suggestions that the ultimate limits on computation might involve black holes, though practical implementation faces overwhelming challenges. While wormholes, time machines, and black hole engines remain firmly in the realm of speculation, they demonstrate the richness of general relativity. The theory allows solutions that challenge our intuitions and push the boundaries of what we think possible. Whether these exotic possibilities have any reality beyond mathematics remains an open question, one that will likely only be answered by deeper understanding of quantum gravity. Chapter 13. The First Photographs of Infinity. In April 2019, a remarkable image appeared on screens around the world, a bright orange ring surrounding a dark center. It looked almost abstract, like a piece of modern art. But this was no artwork. It was a photograph of the impossible, the shadow of a supermassive black hole. The target was M87 star, the black hole at the center of the galaxy Messier 87, a giant elliptical galaxy about 55 million light-years away in the Virgo galaxy cluster. With a mass of about 6.5 billion suns, M87 star is one of the largest black holes accessible to detailed observation. The Event Horizon Telescope, a planet-spanning array of radio dishes working together as a single Earth-sized telescope, had spent years preparing for this moment. The observations themselves occurred over several nights in April 2017, with 8 telescopes at 6 locations observing simultaneously. Then came 2 years of data processing, calibration, and image reconstruction before the result could be announced. What the image showed was exactly what general relativity predicted: a bright ring of emission from hot plasma orbiting the black hole at nearly light speed, with a dark shadow in the center about 2.5 times the size of the event horizon. The shadow's size and shape matched theoretical predictions based on the black hole's mass, independently measured from the motions of stars and gas near the galactic center. The bright ring shows an asymmetry, brighter on one side than the other. This is due to Doppler beaming. The side where plasma is moving toward us appears brighter because the motion boosts the energy and intensity of the light we receive. This confirmed that we're seeing a rapidly rotating accretion disk. The image also revealed the jet emerging from M87 star. This relativistic beam of plasma extends thousands of light-years from the galaxy, visible in radio observations. The Event Horizon Telescope showed that the jet originates from very close to the black hole, likely launched by magnetic fields threading the event horizon and extracting rotational energy. 3 years later, in May 2022, the collaboration released a second image, Sagittarius A star, the supermassive black hole at the heart of our own Milky Way. Despite being much closer, only 26,000 light-years away compared to M87 star's 55 million, Sagittarius A star was actually harder to image. The problem is variability. M87 star, with its enormous mass of 6.5 billion suns, changes slowly over timescales of days or weeks. But Sagittarius A star, at only 4.3 million solar masses, varies on timescales of minutes. The hot plasma in its accretion disk orbits so rapidly that the black hole's appearance changes dramatically during a single observing session. This meant the team couldn't simply take long exposures to build up signal. Instead, they had to develop new techniques to create thousands of snapshot images, each representing a possible state of the system at a given moment, then use statistical methods to identify features that remained consistent across all snapshots. The result shows a similar structure to M87 star, a bright ring surrounding a dark shadow. But the ring has a different brightness distribution, with 3 bright spots rather than the single bright region seen in M87 star. This reflects the chaotic, rapidly varying accretion flow around Sagittarius A star. These images represent far more than pretty pictures. They're tests of general relativity in the strongest gravitational fields we can observe. The shadow size, shape, and properties all depend sensitively on the exact structure of spacetime near the event horizon. Any deviation from Einstein's predictions would show up as differences between the observed shadow and theoretical expectations. So far, Both black holes show shadows consistent with general relativity to within the measurement uncertainties of about 20%. This rules out many alternative theories of gravity that predict different shadow properties. It confirms that we're really seeing the signature of an event horizon, not some alternative compact object. Future observations will improve these images dramatically. Additional telescopes are joining the Event Horizon Telescope Array, improving coverage and sensitivity. Observations at shorter wavelengths will provide better resolution. Eventually, space-based telescopes might create baselines larger than Earth's diameter, achieving even sharper images. The ultimate goal is creating movies, not just snapshots. By observing continuously over many hours and tracking how the emission patterns change, astronomers hope to see the dynamics of the accretion flow in real time. Hot spots orbiting the black hole would appear to move in the images, their trajectories revealing details about the space-time geometry. Such movies could test general relativity with unprecedented precision. The orbital motion of material near the innermost stable circular orbit depends sensitively on the black hole's mass and spin. By tracking this motion, we could measure these properties more accurately than ever before and search for any deviations from Einstein's predictions. The images might also reveal the photon ring, a narrow, bright feature at the very edge of the shadow, created by light orbiting the black hole before escaping. This ring contains images of the accretion disk from multiple angles, including views of the far side of the disk gravitationally lensed around the black hole. Resolving the photon ring would provide an even more stringent test of general relativity. These observations are already revealing new physics about accretion flows and jet launching. The connection between the shadow observations and other measurements, such as infrared observations of stellar orbits and X-ray observations of flares, helps build a complete picture of the environment near supermassive black holes. Other black holes are potential targets for future imaging. The black hole in the galaxy, Centaurus A, an active galaxy relatively nearby at about 13 million light-years, should be imageable with improved techniques. So might the black hole in our neighboring galaxy Andromeda, though at a distance of 2.5 million light-years and with a mass perhaps 10 times that of Sagittarius A star, it presents different challenges. Each new image will teach us something unique about black holes, their environments, and the fundamental nature of gravity and space-time. We're still in the early days of black hole imaging, with dramatic improvements expected in coming years and decades. Chapter 14: The Cosmic Role of Black Holes. Black holes aren't just isolated objects of theoretical interest. They play crucial roles in galaxy evolution, star formation, and the large-scale structure of the universe. Understanding their cosmic impact requires thinking about how they interact with their surroundings over billions of years. The tight correlation between supermassive black hole masses and galaxy properties suggests a deep connection. Galaxies with more massive bulges have more massive central black holes, with the black hole typically containing about 0.1% of the bulge mass. This correlation holds across 4 orders of magnitude in mass, from small galaxies with million solar mass black holes to giant ellipticals with billion solar mass monsters. Why should this correlation exist? The black hole, despite its large mass, directly influences only a tiny region at the galaxy's center. Yet somehow it knows about properties of the much larger galactic bulge. The most likely explanation involves feedback. The black hole and galaxy influence each other's growth through complex interactions over cosmic time. When a black hole actively accretes gas, it releases enormous energy through radiation, winds, and jets. This energy can heat gas in the galaxy, preventing it from cooling and forming stars. Over time, This regulates both star formation and the black hole's own growth. The galaxy provides fuel for the black hole. The black hole's activity affects the galaxy's gas, and a balance emerges. This AGN feedback, named for active galactic nuclei, appears to be crucial for understanding massive galaxies. Simulations of galaxy formation that don't include black hole feedback produce galaxies that are too massive and too rich in stars compared to observations. Including feedback allows simulations to match observed galaxy properties much better. The jets from active black holes have particularly dramatic effects. As they plow through intergalactic gas, they create enormous cavities, bubbles of low-density gas that can extend hundreds of thousands of light-years from the galaxy. These bubbles are visible in X-ray observations as dark regions in the hot gas surrounding galaxies. The energy deposited by jets can equal or exceed the thermal energy of all the gas in a galaxy cluster, the largest gravitationally bound structures in the universe containing hundreds or thousands of galaxies. This energy prevents the gas from cooling and falling into the cluster center, which would otherwise trigger massive star formation. In this way, black holes regulate the growth of the largest galaxies in the universe. Black holes also affect their environments through gravitational interactions. In the dense stellar environments of galactic nuclei, stars that pass too close to the supermassive black hole can be tidally disrupted. The black hole's gravity raises tides on the star, stretching it until it's torn apart. About half the star's material falls into the black hole, while the other half is ejected at high speed. These tidal disruption events produce bright flares that can be detected by telescopes monitoring many galaxies. The flares last weeks to months and emit radiation across the spectrum, from optical through X-rays. They provide unique opportunities to study black holes that are normally quiescent, suddenly revealed by the meal they're consuming. In December 2023, astronomers observed what might be the brightest tidal disruption event ever seen, designated AT2023 VTO. The extreme luminosity and unusual properties suggest that the disrupted star might have interacted with material already orbiting the black hole, creating an exceptionally bright and complex event. Black holes in binary systems with normal stars can also dramatically affect their companions. The compact object's gravity distorts the star, pulling material off its surface into an accretion disk. This mass transfer can cause the star to lose mass rapidly, drastically altering its evolution. In some cases, the mass transfer can be stable, continuing for millions of years, with the star gradually shrinking as its material spirals into the black hole. In other cases, the transfer is unstable, with the system undergoing violent outbursts as material piles up in the disk before suddenly accreting onto the black hole. These X-ray binary systems are among the brightest X-ray sources in the sky. Gravitational interactions with black holes can also eject stars from galaxies entirely. When a star passes close to a supermassive black hole, particularly a binary black hole, it can gain enough energy to exceed the galaxy's escape velocity. These hypervelocity stars travel at hundreds or even thousands of kilometers per second, fast enough to eventually escape the galaxy and wander through intergalactic space. Over a dozen hypervelocity stars have been discovered leaving our galaxy, likely ejected by interactions with Sagittarius A star or, more likely, with binary black holes that may have existed at the galactic center in the past. These stars serve as probes of the galactic center's history and the processes occurring there. Black holes might even affect the formation of new stars in unexpected ways. Hard X-rays and cosmic rays from black hole accretion flows can ionize gas in molecular clouds, affecting their thermal and chemical properties. This could either enhance or suppress star formation depending on the circumstances. Looking to the very far future, black holes will be among the last objects in the universe. As stars burn out and galaxies age, black holes will remain, slowly growing through occasional accretion events and mergers. In the unimaginably distant future, perhaps 10 to the 100 power years from now, when even the longest-lived stars have died, the universe will be dominated by black holes, neutron stars, white dwarfs, and whatever dark matter is made of. Even then, the universe won't be static. Black holes will continue merging, creating larger black holes. They'll slowly evaporate through Hawking radiation, though this takes so long that even stellar mass black holes won't significantly evaporate until after 10 to the 67 power years. Supermassive black holes will last even longer. Eventually, in a timeline almost beyond imagination, even black holes will evaporate completely. The universe will be filled with nothing but dilute radiation, cold elementary particles, and whatever is left of dark matter. But that's so far in the future, trillions upon trillions of times the current age of the universe, that we can barely conceive of it. For now, black holes are active participants in cosmic evolution, shaping galaxies, regulating star formation, and providing laboratories for studying physics under extreme conditions. They're not just endpoints of stellar evolution, but active agents in the ongoing story of the universe. Chapter 15. The Future of Black Hole Science. We stand at an exciting moment in black hole astronomy. After decades of indirect evidence, we've now directly imaged black holes and detected gravitational waves from their mergers. But this is just the beginning. The coming decades promise revolutionary advances in our understanding. Gravitational wave astronomy is entering a new era. The current generation of detectors are Euro, LIGO, Virgo, and Kagra, in Japan Euro, will be upgraded to improved sensitivity, detecting mergers from farther away and with better precision. Next-generation ground-based detectors like Einstein Telescope and Cosmic Explorer will be 10 times more sensitive, seeing black hole mergers throughout most of the observable universe. The space-based detector LISA, planned for the 2030s, will observe supermassive black hole mergers. When galaxies collide and their central black holes merge, LISA will detect the gravitational waves produced by these cosmic cataclysms. This will allow us to study supermassive black hole growth and galaxy evolution across cosmic history. LISA might also detect intermediate mass black holes, if they exist, and even the stochastic gravitational wave background from countless unresolved sources throughout cosmic history. Every binary system involving compact objects produces gravitational waves. The combined signal from all such systems creates a background hum that LISA might detect. The Event Horizon Telescope continues to improve. Additional telescopes joining the array will provide better coverage and sensitivity. Observations at multiple frequencies simultaneously will help separate effects of the black hole shadow from effects of the intervening plasma. Space-based VLBI, with telescopes orbiting Earth, could provide baselines longer than Earth's diameter, dramatically improving resolution. The ultimate goal is movies showing the dynamics of matter near event horizons in real time. Hotspots orbiting just outside the event horizon would trace out the structure of space-time, directly revealing how gravity warps space and slows time. These observations could test general relativity more stringently than ever before and potentially reveal subtle quantum effects near the horizon. Multi-messenger observations combining different types of data will become increasingly important. When a black hole merger is detected through gravitational waves, telescopes worldwide turn to search for electromagnetic counterparts. While black hole mergers don't produce light directly, their environments might contain gas that emits across the spectrum when disturbed by the merger. Neutrino astronomy might also contribute. When material accretes onto black holes at high rates, Nuclear reactions in the hot, dense flow might produce neutrinos. These ghostly particles interact so weakly with matter that they can escape from regions opaque to light, carrying information about conditions deep in the accretion flow. The IceCube neutrino detector at the South Pole and other neutrino observatories might detect signals from active black holes. In 2020, IceCube detected a high-energy neutrino from the direction of a blazar, a type of active galactic nucleus with its jet pointed toward Earth. This demonstrated that active black holes can produce detectable neutrinos, opening a new window for study. Advances in theoretical understanding will complement observational progress. Better simulations incorporating more realistic physics will help interpret observations. Quantum gravity theories, if they mature to make testable predictions, might be confronted with observations of black holes. The information paradox might be resolved through new insights from ADS-CFT or other approaches. Artificial intelligence and machine learning are already playing roles in black hole research. Machine learning algorithms help analyze gravitational wave data, searching for signals buried in detector noise. They assist in reconstructing images from Event Horizon Telescope data and in interpreting the results. As data volumes grow, AI tools will become increasingly important. There's also potential for unexpected discoveries. New types of black holes might be found. Primordial black holes with unusual mass ranges might reveal themselves through gravitational lensing or Hawking radiation. Intermediate mass black holes, still rare in current surveys, might turn out to be common. The first black holes that formed in the universe might have properties different from those forming today. We might discover that black holes aren't alone in accessing extreme gravitational regimes. Some theories predict exotic compact objects like boson stars, gravastars, or other alternatives that could mimic some black hole properties while lacking event horizons. Distinguishing these from true black holes requires precise observations of shadows, ring down, and other signatures. The search for deviations from general relativity will intensify. While Einstein's theory has passed every test so far, we know it must break down somewhere, whether at singularities, at quantum scales, or in some regime we haven't yet explored. Black holes provide our best laboratories for finding these breakdowns. Modified gravity theories make various predictions about black hole properties. Some predict different shadow sizes, some predict different gravitational wave signals, some predict different amounts of energy extractable from rotating black holes. As observations become more precise, we'll either confirm general relativity to ever greater accuracy or discover the first hints of new physics. The coming century of black hole astronomy promises to be extraordinary. We've gone from considering black holes theoretical curiosities to imaging them directly and detecting waves from their collisions. What comes next will likely surprise us, as the best discoveries always do. Chapter 16. The Poetry of the Infinite. As we near the end of our journey through the realm of black holes, it's worth pausing to reflect on what these objects mean, not just scientifically, but philosophically and even aesthetically. Black holes occupy a unique place in human thought, straddling the boundary between the known and unknowable. There's something almost spiritual about the concept, a region of space-time from which nothing returns, a boundary that divides what can be observed from what never can be, a place where the familiar laws break down and space and time exchange roles. The very words we use, event horizon, singularity, black hole, carry weight beyond their technical definitions. The event horizon represents an absolute limit to knowledge. We can theorize about what happens beyond it. We can write equations describing the interior, but we can never verify those theories through observation. Information from beyond the horizon can never reach us. In this sense, the interior of a black hole is more than just far away or hard to access. It's fundamentally disconnected from our observable reality. This touches on deep questions in philosophy of science. What does it mean to have a scientific theory of something we can never observe? How do we validate theories about black hole interiors when direct observation is impossible? We must rely on indirect evidence, consistency with known physics, and the hope that our theories correctly describe reality even in regimes beyond observational reach. Black holes also challenge our intuitions about existence and reality. Does the interior of a black hole exist in the same sense that distant galaxies exist? We can't see inside a black hole, but we also can't see the far side of the moon without traveling there. Yet we're confident the moon's far side exists because we could, in principle, observe it. The black hole interior is different. It's impossible to observe, not just practically but in principle. Some interpretations of quantum mechanics suggest that unobserved quantum systems don't have definite properties until measured. Does this mean the black hole interior somehow depends on observation, even though observation is impossible? These questions touch on the deepest issues in quantum foundations and remain unresolved. There's also aesthetic beauty in the mathematics of black holes. The Kerr solution describing rotating black holes, discovered by Roy Kerr in 1963, is remarkably elegant. The equations describing how light bends near a black hole, how time dilates, how event horizons form, all flow naturally from Einstein's field equations with an almost inevitable beauty. This mathematical beauty isn't mere decoration. Physicists have learned to trust elegant mathematics as a guide to truth. When equations are beautiful, when they reveal unexpected connections and symmetries, they often describe reality accurately. The beauty of black hole solutions was one reason physicists gradually accepted that these exotic objects must exist in nature. Black holes also serve as metaphors extending far beyond physics. They appear in poetry, philosophy, and art as symbols of the unknown, the dangerous, or the transformative. They represent extremes, boundaries, and the limits of understanding. Some find them terrifying, others find them fascinating, and most feel some combination of both. In popular culture, black holes often symbolize death, oblivion, or dangerous forces beyond control. But they also represent mystery, discovery, and the frontier of knowledge. They're simultaneously destructive and creative, ending stars while perhaps forming the seeds of new structures. This duality makes them rich symbols for the human condition. There's also something humbling about black holes. They remind us how small we are, how vast and strange the universe is, how much remains unknown. A stellar mass black hole contains the crushed remnant of a star that once burned for millions or billions of years. A supermassive black hole outweighs millions or billions of stars and shapes the evolution of entire galaxies. And yet we can understand them. Through patient observation, clever instrumentation, and mathematical insight, we've mapped their properties, imaged their shadows, and detected their mergers. This ability to understand phenomena so removed from everyday experience is itself remarkable. Black holes represent the universe at its most extreme, reality pushed to its limits. They're places where our best theories, general relativity, and quantum mechanics clash, where physics breaks down, where new understanding must emerge. They're simultaneously endpoints and beginnings, death and transformation, the simplest objects in nature described by just 3 numbers: mass, spin, and charge, and the most complex, with interiors we may never fully understand. Perhaps what's most poetic about black holes is their inevitability. Given the laws of physics as we understand them, given stars and gravity, black holes must exist. They're not optional or accidental. They're fundamental consequences of how the universe works. In a strange way, they've always been implicit in Einstein's equations. waiting to be discovered, whether we were ready for them or not. Chapter 17. The Journey Home. We've travelled far together on this cosmic voyage, from the theoretical predictions of a century ago to the direct images of recent years, from stellar mass remnants to supermassive giants anchoring galaxies, from gravitational wave chirps to the information paradox. We've explored black holes from every angle. What have we learned? That black holes are real, not just mathematical curiosities, that they exist throughout the universe in vast numbers, that they formed from stars in our cosmic past and continue forming today, that they shape galaxy evolution through feedback and regulate star formation, that they provide laboratories for testing fundamental physics. We've learned that Einstein was right about gravity, that general relativity accurately describes space-time curvature even in the most extreme environments. We've learned that information might not be destroyed in black holes after all, that quantum mechanics and gravity can perhaps be reconciled. We've learned that the universe is stranger, more subtle, and more wonderful than we imagined. But we've also learned how much we don't know. The exact mechanism forming supermassive black holes remains uncertain. The resolution of the information paradox, while promising, isn't complete. The nature of the singularity awaits a theory of quantum gravity. The interiors of black holes remain beyond observational reach. These unknowns aren't failures but opportunities. They're invitations to continue exploring, observing, theorizing, and testing. Each generation builds on previous work, pushing understanding a bit further. The questions we can't answer today will occupy researchers for decades or centuries to come. Black holes remind us that the universe doesn't owe us understanding. It doesn't arrange itself for our convenience or limit itself to phenomena we can easily grasp. Reality is what it is, strange and subtle and occasionally bizarre. Our task is to observe carefully, think clearly, and try to understand as much as possible while acknowledging the limits of our knowledge. This journey has taken us from the collapse of massive stars to the mergers of black holes billions of times heavier, from the quantum foam at the Planck scale to the large-scale structure of the universe. We've explored regions where time stops, where space curves back on itself, where the very notion of here and now becomes problematic. And yet, throughout this journey, we've remained grounded in observation and evidence. Black holes aren't fantasies or speculations. They're real objects detected through multiple independent methods. We've observed their gravitational effects on orbiting stars. We've detected gravitational waves from their mergers. We've imaged their shadows directly. The evidence is overwhelming, coming from different techniques and different wavelengths, all pointing to the same conclusion. This convergence of evidence is what makes science powerful. When multiple independent lines of investigation all point to the same answer, we can be confident that answer reflects reality. Black holes pass this test brilliantly. Every observation confirms their existence and properties. As you drift towards sleep tonight, you might think about the nearest black hole to Earth. It's probably a stellar mass black hole somewhere in our galactic neighborhood, perhaps a few hundred or thousand light years away. It's invisible unless it has a companion star providing material to accrete. It's been there for millions or billions of years, will remain for vastly longer, a silent presence in the darkness between stars. Or you might think about Sagittarius A star at the heart of our galaxy, that 4 million solar mass giant around which our Sun and all its neighboring stars orbit. It's there right now, hidden behind clouds of dust and gas, surrounded by stars orbiting at thousands of kilometers per second, occasionally flaring as hotspots in its accretion disk brighten and fade. You might imagine the Event Horizon Telescope Array, radio dishes scattered across the globe, all pointing toward the same spot in the sky, collecting photons that began their journey thousands or millions of years ago. Teams of scientists working together, combining data, running simulations, reconstructing images of objects they can never visit, never touch, only observe from afar. Or you might think about the gravitational wave detectors, laser beams bouncing between mirrors kilometers apart, sensitive to displacements smaller than a proton's width, listening for the cosmic symphony of merging black holes. Each detection brings news from billions of light years away, from billions of years in the past, telling us about events of unimaginable power and violence. These aren't just scientific instruments, they're extensions of human curiosity, tools we've built to explore regions we can never physically reach. Through them, we touch the infinite, grasp the extreme, and bring the unknowable just a little bit closer to understanding. Chapter 18. The Endless Horizon. Black holes represent boundaries in multiple senses. They're boundaries between the observable and unobservable, between the past and future, between physics we understand and physics that remains mysterious. But boundaries aren't necessarily endings. Often, they're transition points, places where one regime gives way to another. The event horizon is such a boundary. To an outside observer, it marks the limit of the observable universe. But to an infalling observer, it's just another point in space-time, special only because it marks the place where return becomes impossible. The boundary exists, but its nature depends on your perspective. Similarly, black holes mark boundaries in our theoretical understanding. General relativity works beautifully outside the horizon, but predicts its own breakdown at the singularity. Quantum mechanics governs particle physics, but has trouble with strong gravity. The boundary between these theories, the regime where both quantum effects and strong gravity matter, is where new physics must emerge. This boundary isn't a failure of science, but a frontier. It's where the most exciting discoveries often occur, where our understanding must expand to encompass new phenomena. The collision between quantum mechanics and general relativity has driven theoretical physics for decades, and will continue to do so. Black holes also represent boundaries in observational capability. We've pushed technology to its limits to image them, detect gravitational waves from them, and measure their properties. Each improvement in our instruments brings previously inaccessible phenomena within reach. The boundaries of what we can observe keep expanding, but some boundaries may be truly absolute. If cosmic censorship holds, we'll never observe a naked singularity, a place where space-time curvature becomes infinite without an event horizon to hide it. If the information paradox is resolved through quantum effects at the horizon, we might never directly observe what happens to information that falls in. Some questions might remain forever beyond empirical investigation. Does this mean those questions are unscientific? Not necessarily. Science isn't only about what we can directly observe, but about building consistent theories that explain what we can observe while making predictions about what we cannot. General relativity makes definite predictions about black hole interiors. Even though we can't observe them, these predictions are constrained by what we can observe, the external properties, the merger dynamics, the shadow. In this sense, black holes teach us about the limits and possibilities of scientific knowledge. They show us that understanding can extend beyond direct observation, that mathematics and logic can guide us into territories our instruments cannot reach. But they also remind us of humility, that some questions might not have answers accessible to us, that reality might contain aspects forever beyond our grasp. This shouldn't discourage us. Instead, it should inspire wonder. The universe is vast and strange, filled with phenomena we're only beginning to understand. Black holes are among the strangest, but they're not alone. Dark matter and dark energy, which together make up 95% of the universe's content, remain mysterious. The exact conditions at the Big Bang, The ultimate fate of the cosmos, the nature of consciousness, these and countless other questions await future generations. Black holes, for all their strangeness, have taught us that the seemingly impossible can be real. A century ago, most physicists doubted black holes could exist. The mathematics seemed too bizarre, the predictions too extreme. Yet patient observation and clever experiments revealed that nature is more imaginative than human intuition. This is a lesson worth remembering. Our intuitions evolved to handle everyday situations, objects we can touch, speeds we can run, distances we can walk. They weren't designed for relativistic speeds, quantum superpositions, or curved space-time. When we venture beyond everyday experience, intuition often misleads us. But mathematics doesn't mislead. Logic doesn't deceive. When equations are consistent, when predictions match observations, when independent tests agree, we can trust the results even when they violate intuition. This is how we discovered that Earth orbits the Sun despite our feeling of being stationary, that time can slow down, that particles can tunnel through barriers, that black holes exist. Chapter 19. The Cosmic Canvas. Let's zoom out one final time and consider black holes in the broadest possible context. The universe began about 13.8 billion years ago in the Big Bang, an initial state of extreme density and temperature. As space expanded and cooled, particles formed, then atoms, then the first stars. These first stars were massive and short-lived, burning their nuclear fuel quickly and exploding as supernovae. Some left behind stellar mass black holes, the first black holes in the universe. These early black holes, along with possibly more massive seeds formed through direct collapse, began accreting material and growing. Over billions of years, galaxies assembled from smaller structures merging together. Black holes at the centers of these structures merged too, gradually building up the supermassive black holes we see in galactic centers today. Each merger released gravitational waves that traveled through the expanding universe, carrying information about cosmic history. The peak era of black hole growth occurred about 10 billion years ago, roughly coinciding with the peak of star formation. Quasars were common. Galaxies actively fed their central black holes, and the universe was on average more energetic and chaotic than today. Since then, activity has declined. Star formation has slowed. Most supermassive black holes have settled into relative quiescence, their central gas supplies exhausted. Galaxy mergers have become less frequent as the universe expands and galaxies spread out. The cosmos has, in some sense, calmed down. But this is only a phase. In the far future, galaxies will continue merging. In about 4 to 5 billion years, Andromeda and the Milky Way will collide. Countless other galaxy mergers will occur throughout the universe. Black holes will continue growing through these mergers and through occasional accretion events. Looking much farther ahead, stars will eventually exhaust their fuel. The universe contains enough hydrogen to form stars for perhaps another 100 trillion years. After that, star formation will cease. The universe will enter what's called the degenerate era, filled with stellar remnants, white dwarfs, neutron stars, and black holes. Even in this dark era, processes will continue. White dwarfs will gradually cool, eventually becoming black dwarfs, dark and cold. Neutron stars will cool as well. Occasional collisions between stellar remnants will create brief flashes of energy. Black holes will grow slowly through rare accretion events and mergers. After about 10 to the 37 power years, a time so long we can barely conceive of it, even stable structures like galaxies will evaporate. Random gravitational interactions will eject most stars from galaxies into intergalactic space. The black holes at galactic centers will remain, but they'll be increasingly isolated. In the black hole era, From about 10 to the 40 power years to 10 to the 100 power years, black holes will dominate the universe. Everything else, stars, planets, even atomic matter, will have decayed or been consumed. But black holes themselves aren't eternal. Through Hawking radiation, they slowly evaporate. The smallest black holes evaporate first. A solar mass black hole takes about 10 to the 67 power years to evaporate completely. A supermassive black hole of 1 billion solar masses takes about 10 to the 98 power years. These timescales are so vast that calling them astronomical is a wild understatement. Their cosmological timescales raise to cosmological powers. But eventually, even supermassive black holes evaporate. The universe enters the dark era, containing only dilute radiation, photons and other particles stretched to infinitesimal energies by cosmic expansion, and whatever dark matter consists of. Temperature approaches absolute zero. Nothing changes. The universe achieves thermal equilibrium, a state of maximum entropy from which no further evolution is possible. This is heat death, the ultimate fate predicted by thermodynamics for a universe that continues expanding forever. It's a future so distant that it makes the current age of the universe seem like the blink of an eye. The time from the Big Bang to now is only about 10 to the 10th power years. The time until even stellar mass black holes begin evaporating significantly is 10 to the 67th power years, a 1 followed by 67 zeros, vastly longer than the universe has existed so far. This far future might seem depressing, a cold and empty ending to cosmic history, but it's also strangely beautiful. It represents the ultimate unwinding of the universe, the final playing out of physical law across unimaginable expanses of time. Every particle, every structure, every complexity ultimately dissolved into the simplest possible state. And who knows, perhaps even this isn't the end. Some speculations suggest that quantum fluctuations, given infinite time, might eventually nucleate new universes. Perhaps in the infinite future, new Big Bangs will occur, new universes will inflate, and new cosmic histories will unfold. Perhaps black holes themselves, through mechanisms we don't understand, connect to other regions of space-time, or even other universes. These are speculations far beyond current science, but they remind us that our understanding is always provisional, always subject to revision as we learn more. What seems like an ending might be a transition. What appears final might be an intermission. Chapter 20. The Dream of Understanding. As our journey draws to a close, let's return to where we began, the human quest to understand the universe. Black holes represent this quest at its most extreme. They're objects we can never visit, regions of space-time we can never directly probe, yet we've learned to study them, measure them, even photograph them. This ability to understand phenomena far beyond direct experience is one of humanity's greatest achievements. Through observation, logic, and mathematics, we've built theories that accurately describe reality across vast ranges of scale and energy. From subatomic particles to galactic superclusters, from the first moments after the Big Bang to the far future, our theories make predictions that observations confirm. This isn't magic. It's the scientific method. Observe carefully, form hypotheses, test predictions, revise theories when observations disagree. It's a process that gradually, sometimes painfully, converges on truth. Progress isn't always smooth. False starts occur. Promising ideas prove wrong. But over time, understanding deepens. Black holes exemplify this process. They began as mathematical curiosities that many doubted were real. Gradually, indirect evidence accumulated. X-ray binaries, stellar orbits around galactic centers, quasars requiring enormous energy sources. The case strengthened until doubt became untenable. Then came direct confirmation: gravitational waves from merging black holes, images of black hole shadows. What once seemed impossible became not just possible but measured, quantified, understood. This is how science works at its best. But understanding black holes required contributions from many people over many decades. From Michel's dark stars to Schwarzschild's solution, from Chandrasekhar's limit to Hawking's radiation, from LIGO's detections to the Event Horizon Telescope's images, each advance built on previous work. Science is cumulative and collaborative. It's also international. The Event Horizon Telescope involves telescopes on 6 continents operated by institutions in dozens of countries. LIGO and Virgo detectors work together, comparing signals to verify detections. Theoretical work happens worldwide, with researchers sharing ideas across borders. Black hole science transcends political boundaries. This collaboration extends across time as well as space. Current researchers stand on foundations laid by those who came before. Schwarzschild's work in 1916 informs calculations today. Einstein's equations, over a century old, remain our best description of gravity. Each generation inherits knowledge from previous generations and passes it, enriched, to the next. As you settle into sleep tonight, you're part of this continuity. You've joined us on this journey through the science of black holes, learning about event horizons and singularities, gravitational waves and Hawking radiation, quasars and galaxy evolution. This knowledge, hard-won through centuries of effort, is now part of your understanding. And tomorrow, research continues. Telescopes scan the sky, detectors listen for gravitational waves, theorists work on equations, students learn and begin their own investigations. The quest to understand black holes, and through them to understand gravity, space-time, and the universe itself, goes on. Perhaps some listener tonight will be inspired to pursue science, to ask questions and seek answers, to push human knowledge a bit further. Perhaps someone will make a discovery that changes our understanding, that reveals something new about black holes or some other cosmic mystery. Science advances when curious minds engage with deep questions. But you don't need to be a scientist to participate in the wonder. Simply looking up at the night sky, knowing that hidden among those stars are black holes, invisible yet detectable, simple yet profound, is enough. Knowing that we live in a universe strange and beautiful, governed by elegant laws we can discover and understand, is itself a form of participation. Conclusion: where space and time fall apart, we've reached the end of our cosmic voyage, this long journey into the heart of darkness, where space and time themselves fall apart. We've explored the physics of extreme gravity, the formation of black holes from dying stars, the mergers that shake space-time and send gravitational waves across the cosmos. We've ventured to the event horizon, that one-way boundary where the future becomes inevitably directed inward. We've contemplated the singularity, that point of infinite density where physics as we know it breaks down. We've discussed the information paradox, quantum mysteries, and the search for quantum gravity. We've seen how black holes shape galaxies, regulate star formation, and play crucial roles in cosmic evolution. We've marveled at the images from the Event Horizon Telescope, showing us shadows of objects that by definition cannot be seen. We've listened to gravitational wave detectors announcing mergers from billions of years ago and billions of light years away. Through it all, we've witnessed the power of human curiosity and ingenuity. From theoretical predictions to observational confirmation, from mathematics to measurement, we've seen how science lets us understand phenomena far beyond everyday experience. Black holes, once thought impossible, are now among the most intensively studied objects in astronomy. But mysteries remain. The exact nature of singularities awaits quantum gravity. The mechanisms forming supermassive black holes aren't fully understood. The information paradox, while progress has been made, isn't completely resolved. Each answer raises new questions. Each observation reveals new puzzles. This is as it should be. Science isn't about reaching a final answer, but about continuously expanding understanding. Black holes will continue teaching us about the universe for decades and centuries to come. Future observations will reveal details we can't yet imagine. Future theories will explain phenomena we don't yet understand. As you drift into sleep, let your mind wander through these cosmic landscapes. Imagine the bright ring of plasma orbiting impossibly fast around the dark shadow of an event horizon. Picture two black holes spiraling together, releasing in their final moments more energy than all the stars in the visible universe combined. Think about the warping of space-time, how mass curves the very fabric of reality, how gravity isn't a force but the shape of space itself. Consider how time slows near a black hole, how past and future blur near the horizon, how inside the horizon time becomes a direction in space, and the singularity becomes as inevitable as tomorrow. Contemplate the vastness of cosmic time, from the first black holes forming billions of years ago to the final evaporation in the unimaginably distant future. Think about how these objects, despite their darkness, illuminate fundamental truths about reality. Black holes are places where space and time fall apart, where the smooth geometry of space-time becomes infinitely curved, where the distinction between space and time becomes fluid and strange. They're boundaries of the knowable, horizons beyond which information cannot return. They're laboratories of extreme physics, testing our theories at their limits. But they're also reminders of the power of human reason to understand even that which cannot be directly experienced. Through observation and mathematics, logic and creativity, we've mapped the properties of objects we can never visit, predicted their behavior with stunning accuracy, and used them to probe the deepest questions about reality. In their darkness, black holes illuminate the universe. In their simplicity, defined by just mass, spin, and charge, they reveal complexity. In their isolation behind event horizons, they connect to everything, shaping galaxies and testing the laws of physics. They are monsters and marvels, destroyers and creators, endpoints and beginnings. They are where stars go to die, and where, perhaps, new universes might be born. They are the ultimate extreme, reality pushed to its limits, nature showing us what's possible at the very edge of existence. And now, as this long journey ends and sleep approaches, let these cosmic wonders fill your dreams. Let your mind float through the darkness, between stars, past planets and nebulae, through the galactic disk, to the mysterious center where Sagittarius A star waits, patient and eternal. Let yourself fall, in imagination, toward an event horizon. Feel time slow. Watch the universe behind you compress and brighten. Approach that ultimate boundary between here and there, between now and forever. Cross it, knowing you can never return, and drift toward the singularity where all journeys end and perhaps, somehow, begin again. Black holes are where space and time fall apart, but in their mystery and majesty, in the questions they raise and the answers they provide, they bring us together. They unite past and future, theory and observation, the infinitesimally small and the incomprehensibly large. They remind us that the universe is strange and wonderful, that reality exceeds imagination, that there is always more to discover. They whisper that the journey of understanding never truly ends. that each horizon crossed reveals new horizons beyond. Rest now, dream of infinity, and know that out there, hidden among the stars, black holes continue their eternal vigil, waiting for curious minds to seek them out, study them, and learn from them the deepest secrets of the cosmos. Thank you for joining me on this journey to the edge of forever, to the places where space and time fall apart. Until we meet again under the stars, sleep well, dream deeply, and keep looking up at the infinite wonders above. Good night and clear skies.